spices, or in the water industry, like breweries and those kinds of companies, and they use the information we provide them. So we make actually all those technologies we will discuss today and that you are learning about this last week and this week. We make them accessible to new markets. So we're not really traditional. We're pretty small. We often have a focus on sustainability. So we help companies show that they use less water, that their products are more green than their competitors, for instance. So that's what we do. We are based in Rotterdam. Are you familiar with the Netherlands? So Rotterdam is just 15 kilometers that way. I normally go by bike. Of course, I'm Dutch. We're in a very nice UNESCO building. It's an old fabric, an old tobacco fabric. This is our office. Well, we're with 9 at the moment. So my background is in aerospace engineering. So I'm an aerospace engineer. I'm also a biomedical engineer. So I did a PhD in neuroscience, and I moved back to aerospace because data sets are data sets in the end. So I know both from space and from neuroscience. I know a bit. And our team has a lot of expertise. I hope you will notice today that we have a lot of expertise. So we mainly have a lot of expertise, of course, in space technology. Myself, I'm mainly focusing on the data processing and analysis. That's why I'm here today. We build those types of dashboards. So we do a lot of front-end and back-end development. If you'd like, I can show you some live demonstrations as well tomorrow. So we do a lot of interface design, and we think deep about how can we present the data. So of course an image, it can be just an image, but if you want your clients or your customers or yourself to really understand the image, it's not so easy sometimes to really highlight the parts you're interested in. We build businesses around this. So our main targets at the moment are water resource management, land restoration, CO2 offsetting, agriculture and trading, and environmental protection. So for instance, we have a project with the Dutch police where we use satellite data to monitor environmental crime. So there's a lot of intelligence involved. I think that's also really of interest for you. We work all over the world, South America, North America, Africa, Asia, also in Europe, also in the Netherlands. So yeah, a very broad mix of what we do. So today it's all about pre-processing of the data. So tomorrow is really the analysis and the applications. Please, if you have questions, just raise your hand or call me. Just call Thijs and we can discuss. I understood that you have quite a diverse background in your studies and what you have as a background. So if there's anything unclear, just let me know and I'll try to explain it in a different way. As you can see, this is actually what I told you. So the program of today, we start now 9:30, around 12:15. We'll see how quick we are, how many questions you have. We have a coffee break. Interpretation. We go talking about how to locate where your image is, how to correct it, how to clean it, how to filter it, how to sharpen it, and how to interpret it, these corrected images. I guess that's already a lot of information. So if it's information overload, then just let me know. Then I'll slow down a bit as well. There's so much to tell. It's such an interesting topic, I think. So I can be a bit enthusiastic sometimes. So just we are on the same level. I understood that the main reason you're here is that you will be operating a satellite that has an RGB camera, about 45 meters resolution, and that you until today learned about how this camera is working, how the satellite's operating, and that the output is digital numbers, like on this matrix. Is that a bit correct? Yeah. Okay. Great. So I will talk about RGB, but I will also talk about all the other spectra, especially tomorrow, and also about high resolution images. So I will broaden your scope and show you what's possible also with open source satellite data. That's also for you in Thailand freely available. So why image preprocessing? Well, if you have this matrix, it's not very informative as numbers. You want to have like a physical quantity so you can interpret what the pixels mean. So what is actually here on this side? This is water, but you won't know by a number being like 255013, because that's what the RGB bands are. This is a raw image. Of course, we as humans can understand that this is green and this is blue. This seems to be a city, but it's a bit fake and it's hazy, it's dark. So that's why today I'll show you all the steps that are necessary to go to this one on the right, which is after processing. You see that the contrast is much better. You can visually already, as we are looking at this image, better understand what we see. So we actually see more nuances in the water. You see that there's actually something going on underwater. So that already is an indication that it's very clear water, otherwise it won't work. Here in the Netherlands with the sea it doesn't work like this. You see that there are fields. Maybe you can say something about how healthy the crops are on the field. You can say something about the roofs of the houses. And all this is only applicable after image processing. But there are a lot of steps involved to go to this point. So we need to know where on Earth are we, right? We have a satellite orbiting the Earth, but does the satellite say where it is? Can you ask the image, where are you made? No, you really have to calculate it. We have a camera, but the camera is measuring something, but is it measuring the right thing? And there's a lot between our satellite orbiting at 500 kilometers, I think, for you, 550, and the Earth, and that whole layer of air and everything that's in it will affect the numbers we are measuring, and therefore the image. And if we correct for that, then our interpretation will be much better. So that's our next step. What do you see? And of course, with one satellite, it's already a lot of information. It's a lot of data. But as you see, there are hundreds of satellites. Actually, about 1,800 active satellites right now circling the Earth. We do not have access to all of them, but we can access quite some. And all this data, with so many different sources, has its own troubles. And I'd like to start there. So, are you familiar with the term the 4 V's of big data? So it's it's a nice acronym, standing for volume, variety, velocity, and veracity. And those are the 4 keywords if you talk about big data. And satellites generate big data. So the volume, we have, as I said, hundreds of active satellites that we can access. We gather terabytes of data globally and daily as well. It's not that there are swarms, ISIS is working on that as well, that produce daily images, maybe even multiple times per day, of the Earth. So that's a lot of volume. We have a variety because we have lots of sources. We have satellites, we have drones, we have aerial photography, sensors. You can even include media, social media. You have a geographic component as well. So we work sometimes with Twitter data. Twitter data has photographs that you can combine together. I will go into that a bit later. The velocity is often how quickly do the data renew. So how often do you get new information? And as we are moving more and more to constellations of satellites, so sometimes there are just 2 satellites, but sometimes you have swarms of 60 satellites. They monitor the Earth daily with similar satellites, so you can really compare this data and you can get very high resolution in time, everything you want to know about the Earth. And the data is often also sent down to the Earth with using a downlink in near real time. So sometimes you have to wait a day, but currently, for instance, the European Union satellites, they are very quick to send down information and upload it in a portal where companies like Fit2 Impact can use it in almost real time. And veracity, that's actually, I had to look it up. It's a difficult English word. I never heard of it. Of course, I know it, but it's uncertainty. That's a more logical word, right? That's something we all know. So you have a lot of data from a lot of sources, and it's coming at you very quickly. But how sure are we that the data is correct? Because there's a location that can vary. I'll have a slide on that. What are your sensor specifics? Are you actually measuring what you need to measure? So if you want to monitor crop growth, is RGB enough, or would you need infrared, for instance? And if you tell something about crops using your RGB sensor, you can say something about that image, and I'll show you tomorrow. But it's not good enough to measure crops over time. So that's something that you have to take into account. And also, of course, the timeliness. So I made a picture 2 years ago, but is the information on that image, is that still something that's right now at the ground? Or do we need more information? So that's something to keep in your mind. If you combine those 4 V's, the volume, variety, velocity, and veracity, you actually come to the 5th V, and that's what I think it's all about, it's value. So companies like 52 Input, we are called value adders. And that's also something you probably have to do with your satellite. So what is the value you bring to your country using satellite data? And that's something where all this combines into. And then there's a lot of value I think that satellites can provide. And I hope to show you that, especially tomorrow in applications. Because we can do near real-time decision making. With this velocity of data, you can do like event monitoring, weather monitoring, storm monitoring, oil spill monitoring, all those things. There's data-driven intelligence. You can track goods, you can track ships, you can track agriculture. As I told you, you can monitor environmental crimes. And you can apply all those insights we get from the data. So, for instance, for agriculture, forestry, mining is also a very important component. Mines are very large and it's very difficult to monitor them from the ground. But using Earth observation, you can monitor the whole mine, and you can actually monitor mines all over the country and all over the globe. And that can be used, for instance, maybe that's the whole reason that we're here, to, for instance, increase food productivity or and all those kinds of things. Is there a specific topic you are even more interested in than here, so that I can use it in my talk? Is there any direct application that comes to mind for yourself? Intelligence, mainly intelligence. So it's mainly this one and this one. Yeah, okay. So intelligence can be a broad scope. So tomorrow I have a lot of applied insights also from this, but I'll focus also maybe on this.
We would like to focus more on the circle of getting like you said, intelligence information. For example, we would like to know, from the satellite orbit and how to take picture.
Yeah.
How do we get the most out of the processing and the material you're going to teach to get continuously monitoring something.
Yeah. I'll go into that right now, and tomorrow I will be looking more into time series, for instance. So can you use images of the same location over time to monitor fluctuations and monitor changes, actually, because that's a very important thing for. So that's today is that we focus first on getting to the image, and then we go into the application. But that's very good to know. I like to emphasize also for intelligence, and you of course are aware of that those kinds of sources are not on themselves. So you can really combine them. I can show you one example we have for our client that we launched this week, actually on Monday, so 2 days ago, where we combine satellite data and drone data of the same region. So it's actually in Indonesia, people are flying drones there. Why drone? Because the drone doesn't have anything to do with clouds. They fly below the clouds. And our satellite, but it's just an RGB sensor. So we can't say anything, it's for farming. We can't say anything about the health of the crops. That's why we use satellites. With a satellite, it's flying 1 time a day. But it's so cloudy in the region where we are that we only have 1 image per month that we can use. Right? But this combination, where we have drone data once a month, and we have satellite data, it's good enough to actually track the growth of our crop. So that's something you can think about. Also for aerial, I have an example here in the Netherlands. We work for the provincial government. I will show you an example tomorrow of which is intelligence, where we do object detection, car detection, crossing detection. And we were talking with them already for 3 months, discussing where to buy the data. because they said we don't have aerial photography. And then I got an email saying, hey, look at this, we have an archive. Like 2 times a year we fly the whole country with aerial photography. They didn't know. So sometimes there's of course data. You are working in intelligence, so you should know. But think about out of the box. That's something we also see with, for instance, fixed cameras, like security cameras, but also Instagram movies that are geotagged, Twitter locations that are added to photographs, but also mobile mapping vehicles. That's something we work with. So in the Netherlands you have this company, it's kind of like the Google Maps, right? It's just a car driving around. You can combine it by looking down from satellite and thinking, hey, this is, so that's how we often use it. Also, especially I think in intelligence, is that we say, for instance, to the police, hey, here we see a change. We are not sure what it is. We think it might be one of those 3 options. Please go look at ground, or use other data sources if you're remote. So I think if it's something's happening in the north and it's like 5-hour drive, you just say, okay, what kind of information do we have? The same holds for ground sensors. So you can do a lot with satellites, but you can't measure under the ground. It's very difficult to measure soil moisture, for instance. But this can be very interesting to look into, for instance, environmental crimes that are impacting soil quality or forestry. And then some sensors spread out over your fields can help a lot, and you can combine them and even make your interpretation better. So that's something I want to...
just a quick question too. And then one more thing too, we have satellite and also we have some drones. Mm-hmm. So like you said, maybe like the idea of how we use satellite as a, getting data in a big picture, and from there we can send out drones, how the circle of doing that to maybe tomorrow or something. Idea.
Yeah. I'll try to go into that a bit more deeper. Yeah.
Thank you.
Because it's I think the combination of satellites and drones is one. It's perfect. Almost perfect. You need still to fly the drone, of course, but it's so much better than
using where to go. Exactly.
Then just or only drones or only satellites. It's they really enhance the information you get. So I'm not sure how aware you are of those kinds of things. It's our data portals. So I'd like to have some, because this is Copernicus. It's from the ESA. It's the European Union. They launched a lot of satellites, radar satellites, also multispectral satellites. So they have RGB and like 10 other bands. They have satellites focusing on water, so on ocean water quality and ocean water temperature, on cloud temperature, and that data is all freely available. So that's really something. It's called Copernicus Open Access Hub. There's a website. If you Google this or just look on the internet, then you'll find it. And you can just download. This is it's all Sentinel, of course. So you know the term Sentinel? Yeah. That's also something you can combine with RGB. So again, if RGB, which is a bit more easier to process, gives you an indication of change, you can then just locally look into the Sentinel data, which is multispectral, so it gives you a better fingerprint. I always call it fingerprint, because you know a bit more about the materials you're looking at. You can then just download the local image from Sentinel. You don't have to download the whole country every day, or every 5 days actually is the resolution, to get more information. So we used, for instance, for instance, mineral mapping. You can do using this, or at least get a better feel of what type of material that you're looking at. The same type of portal is available for Landsat, so that's the US version of open data. It's still open at the moment. It's called Earth Explorer. It's actually working the same, but the temporal resolution is slightly less. It's 16 days, so what, two times per month? Well, the ESA is every 5 days, so it's a bit better, but we often combine them. If you're in a region with a lot of clouds, you have 2 chances with open data on quite a good resolution. This is 30 meter. This one is, the visual data is even available 10 meters, so it's really good. And then we often combine it with, so those are commercial satellites. We use Planet a lot. It's 3 meters spatial resolution. So it's pretty good. But they, as well as they have what's called world view, they go down to half a meter. That's really good resolution from a satellite. So that's also something you can keep in mind if you want to have more focus. Skywatch is selling this, and so a feature that the Netherlands has is called Satellite Data Portal. So the Dutch government, they buy satellite images like 6 times or 10 times per year, and everybody can use that if you're living in the Netherlands to, for instance, monitor crop growth or anything else. So we use it also for the police. So here there's a short overview of what you have for open data satellites that you can combine with your own data. So you see here if it's still active. So most of it is still active. There's a spatial resolution. As I said, there's about 30 meters for Landsat. Sentinel-2, that's the one I use the most. The RGB is 10 meters, so that's really good. Some bands are 20 or 60 meters. And Sentinel-3, it's focusing on different things, so it's more on clouds and on water, so their resolution is a bit lower. But you heard this, I think, the last days, right? If you're having a worse spatial resolution, often your temporal resolution is better. So because it's flying higher and it's gathering a large view, you can circle the Earth in one day. This is like the fingerprint. We go into that tomorrow. So how many bands there are? Yeah, I think that's something that can really help you. But okay, let's go into the processing, right? That's what we're here for. So this is an important concept. If you want to know where on Earth you are, then you have to think about the Earth being a globe in 3D, and that you're looking at the image as a map in 2D. And that's sometimes not a very easy transition. So are there people here really familiar with the GIS things? And you are? Good. So then these concepts might be very logical. But the Earth is, of course, it's not perfectly round. You have height that can affect your image. But still, we see it as an ellipsoid. So actually a globe, just a ball actually. And to locate ourselves on the ball, we use latitude and longitude, right? So our company, 52 Impact, it's named after our latitude because we're here at 52 degrees north. That's why we use it. And you have latitude from the equator up and down, so north to south, and you have longitude, which is around the globe. You have, with 2 coordinates, you can know where on Earth are we. So that's a very important concept. But if you want to project this on 2D, because all the satellite images I will show you today, unfortunately, are 2D. I don't have virtual reality glasses with me. But you can project this, of course, in different ways, where you want to go from the latitude and longitude to an X and Y coordinate. So that's what we call a projection. You can do that in different ways. You can do a plane, just put your paper on top of it and look at it. That's called here what we call the azimuthal map projection. You can do it cylindrical, so you put a cylinder around it, or you do a cone, and all those projections have different advantages, but also different disadvantages. So this one, for instance, the information here at the north and the south side of the Earth, the globe, they are stretched out, right? So you see this grid, it's really nice, but it's here you see actually that, for instance, this corner, which is the nice square, if you look at Earth here, that's not a square in real life. So that's a distortion. That's something we can correct for as well. If you're living around here, right, then maybe Thailand has its own coordinate reference system as well. So do you have your own map projection locally? Do you know about that? So we have in the Netherlands we have one with a 0, and then it's in Belgium actually, and then we have our own coordinate reference system in the Netherlands. Maybe we think we are very important. Here we see it actually. So this is the most used one. It's cylindrical, but you see this is the distortion, right? So this should be a perfect circle, but here it's elongated north-south, and here it's elongated east-west. And you can recalculate your coordinate reference system. So for instance, the ESA Sentinel reference system is always a very local part of the world. So it's not WGS84, which is that one. But for instance, if we use it for Dutch applications, we recalculate it to the Netherlands. Why do we do that? Because you can use it in meters, for instance. So we can measure distance on a road. And that's very important. Yeah, that's what I said. So there are distortions. This is important. All those coordinate reference systems, there are a lot. They have their own code. It's called an EPSG code. It's from the Petroleum Society. So it's coming from oil drilling back in the days. They, because those companies are working worldwide and they had to use their information without local distortions. So they made all these local coordinate systems and they gave them a name. And they also gave the global ones a name. So if you're getting information, for instance, from Sentinel, and you see it's in EPSG 32627, which is the one of South America, and you want to recalculate it to something in your own region, then you can look at it. Do you have a question?
What is the red circle?
Yeah. So this is called Tissot's indicatrix, and that's the distortion. So this circle and this circle are actually on the Earth are the same size. So this is like, let's say, 500 kilometers in diameter. This as well, and here too. So that's why you see the distortion, right? So here it's okay, here it's small, but those countries they're too large on the map. And here you see that actually it's smaller, but it's spread out east to west. So the perfect map, which cannot exist in real life, because the 3D to 2D projection cannot be perfect. If you would put this on the globe again, then those would all be perfect circles everywhere. But if you make a map projection, then you can use this.
We don't have this picture in our slide.
Sorry, really?
Yes. No. We don't have it.
Oh, all right. I'll check. Good that you say. That's strange. That's something with the PDF, I think.
One more question. Can you go back for the last slide?
Yeah.
Because we changed about the reference. You take a look at the globes, okay, at the middle and
Yeah.
the last one, and the bottom ones, okay. Do we have to change the reference? I mean, for the axis, because you says x-axis is go up, right?
Mm-hmm.
Based on the Earth. But when you project back to the azimuth, we have to change C to Y. Look like this one.
Ah, you did it with exercise yesterday, you mean? So like this is XY and here this XY is different.
Right.
Yeah.
Right. Because you change the reference.
Yeah, it's yeah, exactly. So it's depending on which system you're using.
Okay.
So here 0, 0, 0 is the center of
And
the
the
Earth.
center, yeah, okay.
And here we say it's, for instance, at the equator. So here it's already a different one. So it's important to know per reference system where your 0 is. So for instance, I have, let me see. For the Netherlands, for instance, if I have the Netherlands, where is it? Oh, I can do it differently. If I would make a reference system especially for Africa,
I see.
yeah, then you would put your 0 here, and you have your reference system like that. And
That
then,
means you will have many calculations.
yes,
That's the point.
that's the point.
You change many methods.
Yeah, and you have to know where you are.
Yes.
Yes, that's the. So it's very important to know in which reference system your information is. Otherwise, you can be on a different part of the globe.
It's very not too complicated for, you know.
It is complicated, and it's where we make the most mistakes.
Yeah.
So when you make, like, for example, the Netherlands 00,
Mhm.
so it's more difficult, but you're gonna have the most accurate,
For here, yeah,
right?
yeah. So it works
Distance
the
and
best
everything.
for the Netherlands,
Uh-huh.
but if you go outside, so it won't work. So our 00 doesn't really work again far away because we.
But
are
one
stretching.
meter here is more accurate than using the system that says 00 somewhere else.
Yeah, yeah, because you're far away with those circles again. If this is your 00, then here it's different because you have this stretching and the distortion. Yeah, I can show you more examples later. Welcome, François.
Today I'm a student.
Yes, good. So let's see where we have the satellite. We have a satellite orbiting in space. I won't go into too much detail about this because there's a lot more to say. But you know, of course, from your satellite, you know the height, you know the speed, so you know at each moment in time where your satellite is in space. And you know the time of capture of your image. That's something that's safe. And then you actually use that to project your location back to Earth, and you know where you are, almost. There are of course some errors, I will go into that later, but that's the basis of where you are. So that's something to convert from, I think, is this your drawing actually?
Yes, it is.
Okay, to go from those digital numbers, which are still digital numbers, to at least a location on Earth where you can draw a map, right? That's the important part. How do you really know where you are? You need to do some ground truthing, we call it, and that's called georeferencing. So you really are going to, kind of warp your image, change your image, so it's really where it should be on Earth. How do we do that? Well, for instance, by aligning the data, which is in a coordinate system, to other data that you know where it is on Earth. Think about a cross-section of a road or a church tower, all those kinds of things. And if this is your image, if this is your matrix of digital data, of the digital numbers, sometimes on Earth it can be rotated a little bit. So your satellite is not perfectly going in a straight line, of course. Sometimes you have to warp it. So maybe, for instance, using a second order polynomial, or sometimes even a third order polynomial, so it's really being warped. So that's what we call here the warping HQ. If you do this in practice, you do this using ground control points. So this is your image, right? You see that there's a cross-section of roads, so that's something we know. And this is the image you already had before, so you know where this is. You say, okay, this point should then be located on that point. And you do that on a lot of locations in your image. So you, especially in the corners and also in the middle, so you have to make sure that your whole image has those points. So you do that like this, and you say, okay, this is my map, and those points, so for instance that one should be here, that one should be here, there and there. The very easy one would be to rotate the image, and it's done. But sometimes, as I showed here, so sometimes the best, so this is something that should be calculated, can be done in software. Your transition is a bit more like this, and sometimes it's even more wavy. Why is it? It's also not always the same. So part is depending on your camera, but the part is also depending on how quickly your satellite is flying. And as I told you, everything that's happening between the satellite sensor and the Earth. So sometimes there are distortions there that cause it to move a little bit differently. So what can you use? Well, on margin of image, there are always some elements that are identifiable, like corners of the buildings, solitary trees. So if you're really looking at the plane, like for instance agricultural fields, there are often some highlights that stand out. On your resolution, maybe like a church tower is difficult to spot, so but then for instance big road intersections can be used, or corners of fields, for instance. Right, so that's what we call georeferencing, using ground control points. If you are actually going to do this, then often you need to what we call resample your image. So you're warping it, right? You're rotating it. Rotating can be easy, as you see here, but you are actually translating your pixels a little bit. So you're moving your pixels around in your coordinate reference system. So there are three types of what we call resampling, and they're all a little bit more complex, and they're all a little bit more nicer if you look at it. but they do transform your data. So the values that you measured, so in the original, for instance, here this pixel is black, right? And here it's gray and dark gray. It's if you just rotate it, the pixel is still dark or gray or light gray or black. And you see that here in nearest neighbor there are exactly those values. But if you are going to smooth this, and if you're going to want to have those corners actually really sharp, because that can be something important for your intelligence work where you really want to see sharp corners and know what there is. Here it's even sharper, but remember that the values are altered. So if you want to classify your data, for instance, to a library of values, so with RGB this is often a little less important, I would say. But if you do this, for instance, with the near-infrared bands of Sentinel or the shortwave infrared, then the values you get there are really altered, and their relation together is also altered. So your fingerprint that I talked about is different. But just to go into this, so if you're actually rotating your image, right? This is the original image. This is your corrected, so it's rotated. You say, okay, I have this grid in my reference system. I have this pixel, and I say, okay, this pixel is closest to that one that I want to know, so I just move that one there. So that's what's shown here. Those are the new pixels, you move the closest one there. But it's the real value. So the RGB values you have, so the 255.013, it's still 255.013. If you say, I want to have a bit more sharper result, you can do bilinear interpolation. Then you're not moving one value to the center one, but you take the 4 around it and you do an average. That's why it's a bit more smooth, because you're filtering the data, right? So you just take the 4 closest and you sum them and you divide them by 4 and you get the average. For a convolution, you go even a step further. You do not use the 4, but you use, for instance, the 16 ones. So the image will be nicer, right? It's looking better. If you would like to make nice pictures, use that one. But the value is even more distorted. So how does that look like in satellite images? Well, here it's nearest neighbor. You really see the blocks, right? Or the blocks of pixels. And this is, of course, there's RGB data behind it. Here, if you look through your, you close your eyes and you look at it, you see it's less blocky, but it's also more smooth. And it's depending on your applications, what you're interested in. But this is something that's always happening. But you have to do it because you have to put you want to know where your image is located on the globe, right? So it's a trade-off, kind of, and you have to think about what's important. Do you want to keep the original values at a certain location, or you want a smoother picture with less information? Yeah.
Can you go back one slide?
Of course.
The second one, nearest neighbor. So you near it, like when you rotate,
Mm-hmm.
so you kind of move pixel to the nearest neighbor.
Yeah. So you do this. So the example I have here is always for rotation, and here as well. You can use it for any transformation, but here you just say, okay, I had this location, and using those. Sorry. Yeah.
The dark one is the original pixel.
Yeah, so this is the original pixel, the dark gray one here, that one. And you say, using, for instance, this one, so you know what you rotate, right? Yeah. Yeah. For instance, you go 30 degrees clockwise, you want to rotate it, you know this is my pixel, and I have to move it a little bit around to put it on the map like it is. Then you say, okay, this pixel is closest to that one. It has the highest amount of overlap, so I'll move that here.
Yeah.
That's the easiest way. But you see, this pixel probably has information in it from 4 pixels that were behind it, actually. So that's why you can choose to make an average of those 4. So, okay, that's the value which you have. And this is maybe more to smooth it and to make it a nicer looking picture. So this is actually, it's 3 steps where you can choose. Is it clear? It's a difficult topic, which I understand. So there's one more thing I would like to talk about for knowing where on Earth you are and transforming your pixels. It's called orthorectification. So as we've seen, we have like topographical variations in Earth, right? So we have height differences, which we call relief, and we have tilt from the satellite center, which is perspective of your image. If you keep your camera like this, you have different perspectives than if you keep it straight down. And that affects the distance from where we are taking the image. So if you take your satellite is flying at 500 kilometers altitude, if you take a picture of Mount Everest, you're closer to the sensor than if you do it here in the Netherlands, where we are below sea level. And this change in distance affects, of course, your picture. So what we do with orthorectification is that we stretch this image by taking out especially the elevation and the information about the tilt of our sensor. I'll show you an example of that. So what do we use it as inputs? For the elevation, we can use a digital elevation model. I'll show you what it is. And for the sensor information, we can use something called rational polynomial coefficients. Actually, those are values provided by the sensor deliverer. Maybe François knows more about it than I do, but that's some values about how your camera is tilted with respect to how you make the image, and then you can apply it. So if you look into that, I have an image, an example here from a plane. Actually, you see your plane can tilt, right? Like your satellite can tilt, and your satellite can tilt like this or like this. And you can have a certain height with respect to the bottom, for instance, and all those give coefficients that you can use for correcting your image. This is often done in the software package that you use for correcting. I'm not sure if you talked about this yesterday.
I did some of these topics, but I only mentioned something of the auto-rectification just in very brief overview with some slides saying that this is something you need to do. And then spent most of the time really going into, how do you get from the RGB Bayer matrix sensor to a digital number for every pixel. And we had some real image data from our small 2U satellite that has an RGB camera. That's the same one they have on their satellite.
Yeah.
So just to see how the raw data looks and how to convert it into something you can look at.
Yeah.
But we haven't gone into any more detail on this.
Okay. Well, I won't go into even more detail than this, only for the demo. But this is, it needs something to be aware of, actually. So if you would like to know more about how to really apply it, but I think there's not really time to go into that because we have so much topics to cover today.
Sorry to interrupt.
Yeah.
I told them at the beginning of the course that if you really want to go into detail, it should take 3 years. But
Yeah. Okay.
don't have
Yeah.
3 years.
Exactly. So this is one morning. I read a lot of information this morning. I hope you can all process it. But of course, yeah, it's a topic on its own. Yeah.
I want to add that I don't know how the rest of your course is structured, the part you are giving, but I can give you the real satellite images. They're very small in terms of compared to big high resolution line scan images. So it's only a 2.2 megabyte, 2.2 megapixel file. But there are images that have some recognizable landmarks in some of them. So it could be interesting for you to maybe just see if you can in some way apply it to maybe to one of those also. But if you don't have time, of course, I understand.
Yeah. Maybe we can look in break. Let's take a quick look. What's possible? Yeah. So. I think this is a crash course based on a lot of data, and I'm not sure. Yeah, if you probably might want to use a digital elevation model to correct your images. I think.
Yeah, this is not something that we are currently doing actually.
Okay.
Yes, this is we see this as something for the downstream processing.
Yeah,
we
yeah.
are not involved in that.
Okay. Good.
Yeah.
So then I have to tell you about it. So if you want to know where on Earth which height you have, you can use something called a digital elevation model. maybe you have one of the whole country already based, for instance, on plane flights, on LiDAR. But if you want to have it globally, there has been a space shuttle mission in about the year 2000. It's called the Shuttle Radar Topography Mission, the SRTM. It's a very well-known acronym in remote sensing world. And it gives you a global digital elevation model. So it has pixels of about 30 by 30 meters. And it's giving you the information about how high are we based on the zero sea level. So you can get information about, okay, this pixel is at, let's say, 200 meters, and this one is at 180, and this one is at 160. So meaning you have a slope, and that's very important information to have, because that's actually affecting the brightness value that we're measuring. So it's affecting the digital number that we have. Let me see. So actually, yeah, maybe I'll first show you an image of, I hope this is working. It is, right? Yeah. So here you have an original, and we know that there's actually, in this image, that there's a difference of 1 kilometer between the lowest point and the highest point. And we have a sensor elevation of 60 degrees. So that means that if we apply this ortho rectification,
What is our sensor elevation?
so the sensor elevation is the viewing angle of your satellite. So we are flying, so if this is vertical, then we're looking into it like this. And that's actually very important, because if you have a church tower, let's say we have a very high resolution image, we have a church tower or a skyscraper, and you look up on it from above, you see a square, if the building is square. If you look at it from the side, you won't see the roof anymore, but you also see the side. So the roof pixel square actually becomes elongated. And that's something that we're correcting for here. So you say, okay, it's the same with a mountain. So you have a mountain, right? You look on it from the top, and it has a certain size, right? It's maybe it's a volcano, and it's perfect. It's a perfect cone. So it's a circle with a top. If you look from above, if you look from the side, it will not be a cone anymore. It doesn't seem to be a cone to our eyes, but in general, it is a cone, and that's what we're correcting for here. That we say, okay, we know from the DEM, from the digital elevation model, that there is this, that it's this height. Then we have to shift this image, move it around until it's on top of our cone again, and that's what you see here. So let me see if there's a clear example. So mainly you see it moving around here, but for instance here, this might be, for instance, rice paddies, right? So you see the different lines, so you know that there are terraces. But they're also, they have different height. And that's why here they are more like, they're like this white, and in the corrected image you see them being compressed, it seems. They're of course not compressed, this is the end, is the real data. So that's why it's better to measure in your ortho-rectified image than your normal image. So if you have this, let me see, if I draw here, can everybody see that? So that's what I said, right? If you have a mountain like this, it would look like this, but then if you look from the side, it would look like this, for instance. So this side is a bit longer than it is for real. And if you measure this distance, so it might be, let's say, 100 meters, well, it should only be 50 meters. And this would for instance, be 30 meters. And that's stretching of the image, and that's why we are stretching and compressing. That's what we're actually correcting for using the DEM. I won't go into the mathematics, but this is something you can often put in your program. I will discuss some programs tomorrow. And otherwise, it's something to keep in mind.
Because,
Yeah?
because when you have to transform this one, okay, we focus on the mountain. However, we have to transform for the whole area, right?
Yeah, you transform for the whole area, yeah.
But
But the effect is most visible in the mountains, for instance.
Otherwise, the new picture will have the wrong image. Or something.
It's different. Yeah. So then you have to keep in mind that it seems on your image, on your map, that the mountain is like this, but in real life it's this.
Except unless you focus on the only thing that you're interested in. Something like
And
that.
if you keep it if you're interested in changes, and you keep the image like that, then you can still see that part of the mountain, for instance, or part of the image is changing, but you're not entirely sure where on your map it is, because the map has the mountain like this and not elongated.
Okay. How long you gonna take for the transform from one picture to another picture? For example, you communicate in mathematics, like you said.
Mm-hmm.
How long?
How long it takes for?
Yeah, some kind of this from this picture to from the mountain that you said and go to the real thing that you're gonna show us.
But it's software. It's just a second. So it's really a pre-processing step. That's rather it's easy, but you have to keep in mind that you have to do it to really know where you are on the map. Yeah.
Could you be able to prove with the software that the result is correct?
That's a very good question. If you can prove it, often this is based on visual inspection, but it's also a very common procedure. So it's there's a lot of information if you dive into this.
You have something to cross-check. Like for example, you have image from satellite and then you use software.
Yeah.
You have other sources of information to cross-check that this is actually 1 meter and this is actually something it shows that is.
Yeah, I think that's it's always good to cross-check. For instance, if you have other sources like an Esri world map, another world map, or a previous image, or a aerial photography image that you know is correct, and then you overlay it and then just cross-check the results. It's especially important if you're writing your own code to process this.
So we can use this. Well, if we have the software and after we have the result and we found out later that this is actually need to be corrected, can we input that into the software and to make it adjust the result accordingly?
Yeah. So often, I'm not sure. Are you already thinking about some software to use, or?
I don't know the software you're talking about.
Yeah. So if, for instance, it's pretty sure it can be done in open source Quantum GIS, but for instance ArcGIS, which is a large software package, commercial, you can use that for it. Yeah. And that's already in market for 20 years. Yeah.
For the auto rectification with them, you must have a good quality of them data, right?
Yeah.
So in NASA, you say that it's only 30 kilometers or 40
meters. Meters. It's very
You
good.
need more than this, or just this one is enough?
Often this.
But if you have
really good.
good resolutions of the imagery, satellite imagery, 5 meters or lower than 1 meter, you need a better than, right?
It will affect it. Yeah. So you can do it using this, but it's less good than if you use a DEM of 5 meters. Yeah. Yeah. Very good point. I hope this is clear. That's something to think about. There are of course some errors. These are all approximations I got from the book, but it's the effect of certain parts. So, for instance, and on how far away you are from measuring it. If you add this up, it seems not so much, but in practice, sometimes we have satellite images that are 100 meter or 200 meter or more, off from the point you want to be. But for instance, the satellite clock. Good morning. Satellite clock error, maybe just a second difference in your clock compared to your lookup tables of your orbits is already, of course, affecting where you think your satellite image is. So if you then go looking for your ground points, that would be very difficult. Of course, like I said, the tropospheric effect. There are the ionospheric effect, so that's the different layers in the atmosphere. The ephemeris, so it's like the movement of your satellite is already like making a kind of a blur, and sometimes it's taking more time to make the image and your satellite's already moved. That's also something affecting. I won't go into too much detail because this is a lot of physics, and I will because it's already almost 10:30, and I want to talk to you about radiometric correction. So I would suggest we go into this radiometric correction, and then we have a little bit of coffee break, and then we go into the atmospheric correction, and we do image enhancements, and then we are still on schedule. So why radiometric correction? So I said, okay, there are different challenges in image processing. We know where we are on Earth at the moment, right? Still, we might already have altered our digital numbers by the resampling. But let's say we still have the correct digital numbers, then there are still factors that are affecting the interpretability of our numbers. And why is it important to have the correct interpretation? Because if we want to compare images over time, for intelligence especially, it's very important to know that your images are comparable. So that a number in one image last month is meaning the same as the number right now. Because if there's already a difference, it might be small, then you say, hey, there's a change, but there's no change. And vice versa, it's even worse if you say, hey, there's no change, but that's actually, there's a large change, but your correction was wrong, right? So that's something to keep in mind. And that's what we're going to look at tomorrow. If you want to compare a time series, then it's important. So what is actually going on? Your sensor is measuring energy, light being reflected from the ground. Light is coming from the sun. And there's a lot going on in between the sun and the earth and the sensor. And sometimes the earth is not even reached by light that is measured at your sensor. It's called scatter. And of course you can think that there's of course a seasonal effect in this, because the sun angle is different over seasons. There's an elevation difference here. And of course atmospheric conditions like clouds, rainfall, water vapor, aerosols, smog, they can all affect your image. I will go into this a bit more, but I really like this image because it's showing you like there is a direct, what we call a direct path, and the full path. That's sun coming in, it's reflecting on the earth, and you're measuring it at the center. That would be perfect world. That would be, I would love that. But of course, the atmosphere absorbs energy from the sun. There is radiation that's, for instance, reflecting back upwards and down, so it's not never reaching the sensor. There's sometimes reflections, for instance, like hundreds of meters away, bouncing off. Think about a lake, for instance, and bouncing off here, reaching your sensor, so you're not only looking at that pixel, but you're also getting information from this side. And then there's this light that's never reaching the earth, but bouncing off, for instance, water vapor or clouds, going into your sensor. You think, with all your geolocation efforts, you think you measured this pixel, but actually you measured something from the sky. That's what we're going to talk about right now. So I found this very nice slide. I have sources tomorrow afternoon at the end of my slides. There's a lot of information on the internet about this, but those are the steps. The important words here are top of atmosphere and bottom of atmosphere. So the DM, the digital numbers, that's what Francois told you all about. You recalculate it to add sensor radiance. That's probably something you...
I didn't talk about that.
Alright, I'll talk about that. You do provide some metadata probably about how to convert it.
Yes. I did talk about the fact that we calibrate the sensors usually using an integration sphere on the ground to know that the offsets of the individual pixels are correct for all of those things. So at least that you know that if two pixels are different, it is because of something the camera saw, not
Exactly.
because of something that's happening inside the
Yeah.
camera.
Well, that's already perfect.
Yes.
That's good enough. I'll take over from there. So we have edge sensor radiance. So that's I will go into radiance in one slide. This radiance we can recalculate to what we call top of atmosphere reflectance. So of course your satellite is flying higher than the atmosphere, right? You are in space. We're not in the atmosphere anymore. The atmosphere is already reflecting some sunlight. That's actually what we are measuring, right? It's energy bouncing off the atmosphere and also energy bouncing off the Earth and everything in between. So we have a top of atmosphere. It's depending on the distance between the Earth and the Sun, for instance, the angle of the Sun, and something we call exo-atmospheric irradiance. So how much light is being sent out by the atmosphere. But you want to go to reflectance of the Earth's surface reflection, because that's where interesting. Your intelligence is not taking place at 100 kilometers altitude, I think, but it's happening on Earth. That's why we do atmospheric correction, taking into account all the knowledge we have from different layers of the atmosphere, and you can make that as complicated as you want or as simple as you want. And often it's something in between. There's no need to make it too complicated, but you have to do some corrections. Alright, irradiance, radiance and reflectance. Those are words that are important, but they look like each other, but they are slightly different. So irradiance is the total quantity of incoming light from the sun, right? So that's this part. This is overly simplified, of course. Radiance is something we measure. We often have an abbreviation L. It can be anything. So it can be light from the sky, it can be absorption from the ground. Slightly similar picture. The radiance at the pixel, you can calculate it by using your digital number. You multiply it by some type of gain, and you add the minimum value of your sensor, actually. And that's something that's probably provided. Your gain is it's a scaling factor. So you do the maximum value your sensor can have minus your minimum value. Often, and I think that's 255.
Yeah.
If you have RGB.
I told them that the sensors that we use usually actually output 10-bit data, but for the purposes of getting a beautiful RGB image and the way in which we compress it, we usually supply this as 8-bit data,
Yeah.
so then it's a 255.
Yeah, good. So actually, it's recalibrating your data so we are in a range that we know we want to be in, and that's by using the gain and the L-min. So just making certain that we are in this range of 0 to 255 in this case. And then if we go to reflectance, that's for instance something with the Sentinel images where we know all the steps. For instance, to go from the radiance to reflectance, it's a value, it's a difference of 10,000. So we just divide the number by 10,000 and we get a top of atmosphere. And to go then to bottom of atmosphere, it really depends, the reflectance depends on, for instance, the surface type. That's why we're doing satellite imagery, right? You know that a house reflects differently from a field, and a field reflects differently from a lake. And that's the information we want. And how reflective a house is actually independent of the type of weather. But the weather is, in the end, reflectance is between 0 and 1. Oh, I see my sentence. I'll put the sentence. I'll make it complete. This actually, if you have your values between 0 and 1 as a reflectance, that's the most perfect way to compare over time, because it's so compressed, the information. So that's why we often go to reflectance. And this radiance, let's see, let's first go at, because this is going from radiance to, here we calculate the reflectance. This is actually the correction for the sun and elevation, and it's a bit for camera angle, but it's mainly for sun angle. So you see there's a sun angle, zenith angle is theta. Your sun is at a certain distance, so that's the distance from Earth. Often you use the distance from the Earth center to the sun. this very small bit of the diameter of the Earth is nothing compared to this distance, so we just regard it. And you see here the atmospheric irradiance of the sun at certain frequencies. So we know for R, G, and B, there are certain frequencies in invisible light, and near infrared has another frequency. So those are dependent on the band you're looking into. And then this is the formula we use to actually, we would like it to measure the radiance, but we would like to know the reflectance. So we recalculate the reflectance from the radiance. That's the one we measure. We multiply it by pi and the distance squared. So you see that that's already very important. There's an effect of how high your satellite's flying. And we divide it by the angle and by the irradiance that we know from this band. So those are the factors that we take into account to correct for sun angle.
So to do this, you need to know like the sun angle from the satellite, right?
Yeah, so that's something that you often know from the orbit and the time you're taking this image.
This is one usually done on board, I mean on the satellite? Or you just have like the data and then...
So sometimes if you have already processed a little bit pre-processed data, you know this, but otherwise you can look it up, for instance, because you know that the time of day you're looking at, it's different for different seasons. You can have tables from, okay, at this location the sun angle was this at that moment, so then you have to combine it yourself. Yeah, and again, that's also something some software packages include as well. So if you really have to raw data like you have, then this can be used. For some, like the open source products I showed you at the beginning, then often this is already included, this information. It's actually good. I'll go into this in a few slides. So it's not something you use always. It's depending on what you want. Hey, Mark. So this is some corrections you take a little bit an easier correction where you do not take into account this angle, but it's still better than doing not any correction. And I'll go into that in, I guess, 5 slides after the coffee break. I'm going to first finish those slides, and then we go into a bit more depth there. Let me see how many slides. Yeah, 2 slides more, then we have a break. Perfect. So, of course, Francois is only selling perfect cameras. But it has been seen in history that NASA, for instance, they had a very expensive satellite, Landsat number 7, and there was so it's I'm not sure. Are you using the same mechanism in the Gecko?
Of what?
Of the bands. You have different bands in your sensor, and one of the cells can feel and you get stripes.
Well, no. Actually, on the Gecko, it is a matrix RGB Bayer imager, but on many of our other imagers, including, you could build the Gecko in this way, but we haven't yet ever delivered one of those in the line scan configuration. But we use on the larger imagers, there's one called the Chameleon imager, which I have, actually it's on the table there in the lobby if you want to see it at some point. That can be, that is in most cases considered as or built as a line scan imager. And we have also built even larger imagers. There's one called the Tegu, which is 2-meter resolution. And I actually have some data from that, and that is multispectral line scan. So we have, in that case, on the one we have in space, it's pan RGB, but we can support up to 8 bands, so worldview 2 type bands. So I know that these guys here are talking about their next satellite as well, which will have a 5-meter ground resolution.
Oh wow, cool.
And that they're already doing it next year. So, and that one will definitely, of which we hope that we will be the people to build this imager. But we have to, that is still to be decided. But the point is, those kind of images, they definitely all work as line scan imagers, even though they have matrix sensors. I explained, there's a picture up here on this corner of how we build it. So we have the blue rectangle is the matrix CMOS sensor, but then we have physical glass strips that we place across the sensor, and we read out only some of the lines that are underneath, enough to build up each of the color bands as you go across. And the number of bands you can have is mainly limited by the number of filter strips that you can fit onto the sensor.
Yeah.
Yeah.
Cool.
Can I have you two for a second? You're from Gecko. Gecko is like to build the camera for the satellite, for my satellite, right?
For this satellite,
Right,
yes.
okay.
Yes.
And for it to be impact like you are the image processing, try to interpret something that sensor satellite get the data, and you share it to the YouTube picture or anyone, right?
Yeah.
And ISIS integrates YouTube with the physical satellite in order to get the satellite like this one.
Yes, so ISIS builds the complete satellites,
Yeah.
and they do many parts of the satellite system as well, but they don't do cameras, they don't build that. So if you want to have a camera on your satellite, they have to buy the camera from somewhere, and this is from us.
Okay.
And our engineers, we don't have enough people and resources to do these things,
I see.
so we build the camera, and then we say, okay, there is the camera,
Okay.
and ISIS puts it all into one satellite, but then even ISIS or us, neither of us are doing these things, because we just want to know that the camera works the way we built it and that it is not broken and that it's focused correctly, and then we are happy. And ISIS says, okay, the satellite, the camera is working as part of the satellite and we can download the image, good, but then you still want a beautiful image that you can show to your boss and to your customers and saying like, look, this is what our satellite does, but there's still that gap of you download the file, now you have the raw file, and you cannot show it to anyone, and you somehow figure out how to display it, and it doesn't look really pretty, it's all dark, and there's maybe a stripe going across it, or it doesn't match up, and then you can say, you are bad people, you gave us a broken camera, but it's not. They all work like that, but you need someone like Thijs
You send the data to the
to make it look good.
and
and
to
correct.
use the application to convert, transform anything to be the good picture.
Yeah.
Okay. Because before we leave today, we three, you and us together, have to discuss one thing, one big question that people ask us a lot. What we got it from? What we gonna get it from the sky, from the satellite, raw data, JPEG, and how it's work. And then if you say raw data, we have raw data. What application do we have the software to convert anything? That one is we bring this question to here in order to make us clear and make others clear in Thailand after we get back. This is a key.
Yeah.
So that's a conclusion. Not now. But you continue your this one. It's okay.
Yeah.
Okay. Please, thank you so much. This is a really important thing for us.
It's really great to hear that you're planning on getting another sensor next year, because that's really in the line of all the applications I will show you tomorrow, with 5 meters and maybe even more bands, I guess, as well. So not only RGB but also near infrared.
That gonna be the basic information for us for the next camera in the next satellites, and the idea for the later satellites.
Yeah.
Yeah, I haven't actually seen the specifications that they want for the new.
Oh, okay.
I can speculate on what can be done, so I know what we can build, but.
And also, you know what, people just ask, can you have the example of the thing that we're gonna get it from the satellite? That
Yes.
one, for example, not I know that it's not exact picture from image from the sun, but anything they can show. This is a 40 Met, Gecko camera, this is 5 Met, that to come. What is different? How to improve it by your to impact.
During the break, I can show you
Okay.
some of the images from the Gecko imager we have, and then maybe something I can show you actually some up from the 2 meter data also.
Yeah.
So, but then you have a better idea of what we're talking about.
That would be great. Yeah.
And what you can do for us more after we get the raw data or just JPEG 2000 whatever, and we can have the ideas.
Yeah.
Big boss is sitting here to waiting for the make decision. Okay, you understand that? Thank you.
Yeah, so no, it's a very good remark, and we go into that tomorrow as well. But indeed, if you have, I'll do this quickly before lunch for the coffee break. So of course you have a sensor. It can be a little bit distorted, like you have a camera, you have a normal camera here on Earth, you have also like distortions due to your lens, right? So you correct it, for instance, in Photoshop. That's something you can do here. We often don't do this. We just say, okay, we take the image as is. But those three are important because if you use a light scanner, then each line can have a different gain, and that's what we call striping. So you see that actually every, let's say this is like 8 lines, every 8 line has a slightly different what we call tone, so just a slightly different color compared to the next one, and that's why we have to filter this data to get rid of that, or apply, for instance, corrections per band for every 8th band. That's perfectly fine. What's worse is black stripes in your image, because that's meaning that your camera is broken. So what those images have of Landsat is that they're at every 10th line it's black. It's not meaning that you can't do anything with satellite, because you have 90% of your information, it's correct. But we can use filtering and averaging to correct for that. And there's something called random noise. Just there is speckle. That means there are photons just flying around and just hitting your sensor, and that's random noise, and that's something that can be easily filtered out, of course. That's something I'll go into after coffee. Just as a last slide. So this is this Landsat image. You see the stripes, right? It's perfectly regular. You see it also here in the information. They're just returning zeros, digital number 0. What we can do, the easiest way to do this is just say, okay, this line, that line, we just average it. We just average it and put it here. It's almost average. Here, 86, 88, I would put 87. Because there's a very small chance that there will be a very sudden increase, right? It's nature. There's no such a big increase. So this is the same with resampling. You are actually creating new data, but of course there is meaning behind your created data. It's not that you make this up. There's a certain logic to it. So that's why we do it here. Of course, here you don't see the bottom one. But of course this is also average, so probably this pixel here would have to be 92, so the average would be 90. Those are quick ways to just remove this kind of distortions.
So when you average it in this only,
Yeah.
not like all kind of average?
You can make it as complex as you want. So it's the same with resampling. So here you would only take, if we want to measure that pixel, the easiest way is to do the average of that one and that one. But you can also say, okay, this one should be the average of those 6. And then it's already, it can be a bit better. You don't know, you have to test it and also maybe check with other
So the way the program like doing this is all kinds of things, right?
Sorry?
The way the software, solve this problem is because it's line.
Yeah, it's line. Yeah, so you read the line by the
Yeah,
file by
so
line.
the missing line, you just average,
Yeah.
like vertically,
Yeah, it's
pretty much.
It's spatial averaging. Yeah, it's de-striping, we call it.
Describing.
De-striping, because you remove the stripes. And that's I will show you a little bit more like these kind of operations, the filter operations. But this is the easiest thing you can apply. So if something might go wrong, then you still have. So 90% of the data, even more, it's like 20 lines. So you have 17 lines, something. So over 90% of your data is there. So you don't have to say, okay, my satellite is broken. So it's a little bit broken, but it's not useless. And that's something to keep in mind. Let's have some coffee. If you have any questions, just pop over here. Then after break, we go into the atmospheric correction.
Yeah, I quit during coffee to bring you up to speed on, on the camera stuff. So that
would be good.
Wim, morgen ook nog trouwens dit ontmoeten.
Ja, inderdaad. Ik ben blij.
Ja.
Ik mag even water.
Jullie hadden dat minder goed uit het hoofd, maar ze zullen allebei weten wie het is.
ไม่ให้ถามเลย
มันรู้ว่าพี่จะถามนะครับพี่
ถามดีฮะหรือได้รางวัลขอบคุณตามที่เป็นขอโทษของที่บนต้องไม่ต้องอะไรเจ็บมัน
นั่นเองชั่วโมงหน้าถามไม่เดียว
แต่ถ้าเกินที่15ปั๊บโดนตัดเลยนะ
ไม่ใช่อะไรนะนี่คือเนี่ยจบแล้วซองขาวแล้วพวกมึง
พอสองขาว
อัตราเพื่อพายจะไม่มีชื่อจริงเลย
ต้องใช้โปรแกรมเมื่อวานที่เราลงแข่งไปได้ตัว
มันคำนวณอะไรมาเป็นตัวเลขมันคำนวณเป็นตัวเลข
เราจะมีเลขหน้าจะหา255ที่เราจะตัว RGB
คือที่มันสอนนี้ยังไม่มีในเฟสแรก
คือปัญหาที่
มีซอฟต์แวร์
เราไม่เชี่ยวชาญซอฟต์แวร์ขนาดที่เราจะเรียก
ไม่ทุกอย่างคนที่เป็นซอฟต์แวร์เนี่ยเราจะต้องเจ็บด้านนี้ก่อนเลยแต่ถ้าเราไม่รอดัตต้าแล้วเราอิดนอนอิดเราไอเนี่ยยูนิฟอร์มจิตเนี่ยพวกนี้เป็นเห็นไหมเนี่ยตอนนี้เป็นทัสวันไปทุก
สเต็ปแรกที่เขาบอกเลย
อันแรกอะไรไอ้เนี่ยที่มันทำที่หลัง
แต่พี่แบบอาจจะไอเดียของเรื่องเนี้ยพี่ไม่แม่นไงพี่ยอมรับแต่ว่าแต่ไอเดียเรื่องของจิตตรงนี้โอเคยูนิฟอร์มจิตนอนยูนิฟอร์มจิต second order third order รู้แล้วแต่แม่งคือพี่นานแล้วของมึงโคตรเจ๋งคือพี่มองว่าพี่มึงพูดไม่ได้อยู่เลยที่จะมองพี่ก็รู้วิธีการเอ็นลบหนึ่งเอ็นบวกหนึ่งเอ็นบวกถึง2อะไรเนี่ยแล้วก็ทำพี่กูยังทำตัวไม่รอดไอ้พวกที่มันทำขายตัวไม่ชี้มันทำขายแล้วมันก็ต้องมาเจอยูเซอร์ที่ต้องถามมันแล้วกูจะรู้ได้ว่ามันคนนี้จะได้บริษัทนี้กูคิดไม่ถึงว่าคอนเซ็ปต์แล้วมันจะรู้ได้ยังไงว่าหลังจากเปลี่ยนน็อตขึ้นบ้านให้เปลี่ยนหรือเปลี่ยนน็อตไปเรื่อยๆมันก็ไม่แตกต่างอะไรจากเนี่ยเองเปิดตัวเองเส้นนี้ไม่เท่ากันเองเส้นความสูงของนี่ไม่เท่ากัน
ดูแล้วที่กลุ่มเราเขาแบ่งให้เราทำสรุป
เพิ่ม
เล
ได้
ย
อีก
ครั
ภาษาไทยเนี่ย
พี่ได้
2ตัวนี้ขยายด้วยเรโชเดียวกันยุคนั้นไม่ได้เราต้องหาที่บ้านแบบขยายแต่บ้านเพราะนั้นหมอแค่
ที่กับของพี่เป็นใช้โปรแกรมไงไอ้ไวเชอร์ทอมที่
บ้านไม่เข้าห
แค
ม
ป
อ
เจอร์นั้นนะ
ซึ่งเดี๋ยวไม่ได้ซึ่งคำถามเรื่องเป็นคำถามดีเพราะนั้นมันต้องย้อนกลับ
แต่ว่าแต่ละคนเป็นหลายเรื่องนะ
ที่ภาพคือเนี่ย
มันจะอธิบาย
ถ้ามึงไม่เฉพาะเจาะจงสี่เหลี่ยมเข้าไปเลยคือว่ามึงต้องใส่ทั้งหมดใช่ไหมมาตอบ
เด
เด็
สไบ
พอเชื่อสมมติมีเยอะฟีนอมที่มึงจะต้องมาเขียน
มันเยอะมาก
นี่ไม่ได้จังไม่มึงจะต้องเป็นไม่เท่าไหร่กูเท่าไหร่แล้วมึงทานโพสทีเดียวอินหมดทีนึง
พูดเรื่องแต่ว่าสรุปเราเนี่ยคือ
วันแค่ใช้ซุปเปอร์คอมพิวเตอร์แต่เรื่องบอกว่ามินิเป็น
หน้าบอก
เรื่องฟอร์เซ็กไฟเข้าไปกันว่าแล้วมึงรวมมึงเป็นคิวเป็นอีมาเรียบร้อยแล้วแล้วมึงแค่ใส่ตัวเลขที่ผมต้องการแล้วเราได้ต้องเอารูปภาพละนะ
คนที่ทำต้องรู้ว่าคืออะไร
แน่นอนก็กับการต้องมารู้สูตรก่อนเพราะเขียนสูตรเอาสูตรเป็นซอฟต์แวร์เอาซอฟต์แวร์มาแล้วก็เอาไปวอลิเดตเอาซอฟต์แวร์วอลิเดตพอวอลิเดตเสร็จยูเซอร์เอาไปใช้เลยวอลิเดตเลยแล้วสีจะรู้ได้ยังไงน้ำทะเลถ่ายมาน้ำทะเลหมดแต่เองคนหมดแต่ว่าไอ้โลหะต่างๆมันเก็บความลึกมันเก็บอะไรไว้ที่ก่อนแต่มันทำยังไงมันจะทำฟอร์เป็นสีฟ้าอ่อนฟ้าเข้มฟ้าลึก
ไอ้แกบอกซ่อม
แต่คำถามเบอร์เป็นคำถามดีนะเมื่อกี้จะรู้ได้ยังไงว่าแน่นอนท้ายสุดนอกจากนั้นก็ต้องไปเปรียบเทียบบริเดนกับแบบเรียน
อาจจะ
เป็นคำถามยาว
คนเรามาคอสเช็คกับพวก UAV อะไรนี่
ใช่สูงแต่เมื่อกี้อธิบายแล้วเนี่ยมันอยู่เทียบพวกที่นั่งเลยที่ดีเนี่ยตอนนี้คือพอจะทำแบบนี้มันได้เงินได้นี่ถึงทำทั้งภาพที่มีต่างจะลบแต่ถ้ามาทำเฉพาะที่เราบ้านจะมีแล้วถ่ายในบ้านแม่บ้านเป็นคนท้องแท้เราแค่เดียวเดี๋ยวปืนขยายภาพ
คือเขามีอยู่แล้วคือเขาจะใช้จะใช้ point matching นะพี่เหมือนแล้วก็แบบบีบ
เข้าใจบริขึ้นว่า
ทำยังไงก็ได้
ไอ้เนี่ย
ครับ
คือที่นับถือมันนะเรื่อง
ยากใช่ครับพวกนี้เก่งพวกนี้ยาก
คือไม่งั้นมัน
ก็เอาคนที่สูตรลาดตระเวนที่เขามีโปรแกรมที่เขาใช้อยู่อะ
คือไอ้โปรแกรมแบบพี่โอเคอ่ะที่ถามมึงสองคนเป็นใครแล้วมาทำอะไรมาเอามาทำภาพไอ้นี่แม่งกูว่าทำเซนเซอร์อย่างเดียว
ใช่พี่ก็คือมันไอ้นี่เซนเซอร์อย่างเดียวทำเซนเซอร์ดีสุดนี่รับต่อมาทำยังไงก็ได้ให้มัน
ไอ้นี่ก็เอา data มาอย่างเดียวคิดแต่ data อย่างเดียว
ใช่ครับ
โอเค
เพราะ
มั
ว่าน
เอา0010มาอย่างเดียว
ใช่
เอามันในรูปของ magnetic wave magnetic ไอ้นี่ตัว magnetic
ครับ
ใช่ไหมมาเอาแสงตัวเนี้ยมาเป็น00
ใช้ได้ครับพี่ เพราะว่ามันเป็นองค์ความรู้ที่ใช้ได้มันต้องใช้หลายอันมาประกอบกันให้เกิดออกมาแล้วคอสเช็คให้ดีอย่างเงี้ยถึงจะได้
เดี๋ยวเราจะส่งคุณมาเรียนโทเรียนเอกวิชานี้กัน
พี่บังเรา
คุณโชคถ้ามึงไม่เข้าใจแบบนี้
ก็นี่เมื่อกี้ไม่ได้บอกเลยไม่เป็นไร
เหลือแค่ชั่วโมงเดียวนะ
จะมาลงคือต่อที่มึงแทน
เดี๋ยวคุยกันยื่นซองไว้เดี๋ยวหยิบโนตารี่แล้วมีตัวประกัน
ใส่กัญชาเข้าไปให้มันคุยกันเมากัญชา
หยิบโนตารี่แล้ว
ผมแค่คาดหวังว่ารู้จักชื่อมันแล้วก็เก่งกับพวกเราทำอะไรก็เก่ง
เดี๋ยวเวลาเขาอายเป็นเฉพาะกลุ่มก็ได้เขาอายทั้งลูกก็ได้
ก็เหมือนตอนที่มันทำกับแกแล้วเลยนี่ที่หนึ่งเดียว
ที่มันที่คอมใช่ไหมเอ้ย TBS เนี่ยพิมพ์ก่อนครับทำในทีวีเปิดนี่เนี่ยแบบ
แต่ที่จริงโปรแกรมที่เขาถ่ายแล้วทำเป็นโปรแกรม
อยู่ในเซตติ้งแก
ส่งมาในนี้ดีกว่าไหมส่งมาในกันเดียวซีให้กันไปส่งไปใหญ่
ดูเพื่อเป็นไฟล์ธรรมดา
เนี่ยหรอก
ดูหรือว่าไม่ได้
ส่งมาในเข้า
ต้นมันลายดอกได้มันเอาดอกใส่ผมก็พายมันดอก
เดี๋ยวเรา
คือขนาดผมรูปในลายอ่ะผมเซตว่าให้มันแม็กซิมัมครับรูปที่ส่งในลายคือส่งไม่ได้ตามกล้องมันไปปุ๊บ
ลือแล้วซอฟต์แวร์นี่มันมาด้วยป่ะขายของอยู่ใช่ไหมเนี่ย
แต่ว่ามันก็ดีให้เรารู้ว่าสิ่งที่เราจะต้องแต่ว่าพวกเนี้ยมันไปอยู่ในส่วนของที่น้ำอะผมเห็นที่ผมโปรแกรมซื้อเลยแต่ว่าเสร็จหน้ามีให้นิดหน่อยเองก็สูงโอกาสเข้าทางการจะมาแต่ไม่รู้ได้แค่ไหนก็ตามเพราะเมื่อวานที่ตัวความชัวร์มันต้องมาไอ้เน็ตโปรเซสซิ่งมันหลายระดับนะคืออันนี้เรายังอยู่ระดับหนึ่งอยู่เลยหนึ่งกับหนึ่งอ่ะ
อากาศเย็นนิดหนึ่ง
70 เดี๋ยว30
เย็นเย็น
เอาไปทอดลงรถแกะข้าวสารไม่หมด
มันพอเลยนะพี่ซองนะได้ไหมเนี่ยถ้ากระเป๋าใบใหญ่ไม่พอเอาจริงมันกระเป๋าใบใหญ่ที่เหลือเท่าไหร่เองนั้นน่ะ
สิบสี
ไม่ต้องละ
เสียไก่เสียไก่เสียเบอร์เสียรวยหมดทั้งหมดที่ผม
ใบใหญ่ที่วันนั้น
พี่เอกห้ามเหลือนะพี่
ใช้หมวกห้ามเหลือ
เพราะถ้าพี่เอกครั้งนี้พี่เอกซื้อต่อไปเยอะ
โดนที่ชิงที่หนักบิน
สนามบิน2 อันได้พี่
อันไหนเนี่ย
วันนั้นเนี่ย
2 ต่อด้วยนะ
ต่อเลย
แต่ถ้ากระเป๋า
แต่ตอนนั้นพี่เอาใส่รวมมันเลยเพราะว่าโหลดใต้เครื่อง
จำได้ว่ามากกว่า1 ใบแต่นี่มันไม่ยอมเขียนชัดเจนเลยนะว่า1 ใบ
นี่น่าจะเป็น KLM ที่แล้วมันของ
มีว่า
จะบ้า
จำได้ว่าคราวที่แล้วเนี่ย
พี่เอก30
คือมันบวกกันไม่เกินใช่ครับบวกกันไม่เกิน
30นะเท่าไหร่
ได้บวกกันไม่เกินแต่นี่มันเขียนเลยว่า1 กระเป๋าพี่ก็ไปถามที่เคาน์เตอร์ที่เมืองไทย
เพิ่มอีก4 ยูโรให้ถ้าเกิดว่าเพิ่มเหมือนไอ้ที่ผมโลคอสซื้อได้ถ้าไม่เกินกี่ยูโรแต่ถ้าเกิดจะเพิ่มกระเป๋าจ่ายเงินเพิ่มอีกสัก4-5 ยูโรเงี้ย
พี่ลือเดี๋ยวขอจบคอร์สรูปงานชีวิตทำงานแล้วนี่แสดงว่าเราต้องใส่ได้อีก2 โล
ครับใบใหญ่ที่260
เดี๋ยวพี่เบอร์จะเอากลับยังไงพี่เลยมีใหญ่
อะไรนะ
กล่องคุณ
การไป100เต็ม500แต่50เรื่อง
ไปใหญ่เลยทางน้องก็คือ
ทำความรู้จักกับคนที่สนามบิน
เราส่งยกกระเป๋าคุณจะซื้อกล่องนั่นแหละ
เอาของทิ้งนะ
ใบใหญ่ที่พี่ต้องซื้อนะครับเพื่อจะเป็น2 ใบ
ใช้ได้เยอะด้วยนี่ใบใหญ่
ก็ใส่
Often, if you really look at the
ซื้อได้เลย
statistics,
มาซื้อตัวไหน
every, like if you have a bowl of energy, it's
เด็กก็
everything, in every
ซื้อ
direction.
หนักขึ้น
Radiance is like you have a plane, and it's coming in.
หาของใส่
So you say, okay, I measure it at this plane. That's why it has this per square meter in the
เอาพวก
here per
เสื้อ
square.
ผ้า
So
ถุง
this
เท้า
is
ที่
just, it's all per radian, it's all directions.
แต่เสื้อผ้าที่เอามาเราก็
With a plane. So with a sensor, for instance, your sensor is a plane. And the light falls
ประ
on
มาณ
it,
20 โล
and then and that's what
มันต้อง
converts
มีมาม่า
this
10 โลนี่
So that's what we call it once per radian per square meter.
ปกติไปเมืองนอกนี่คือแบบว่าอัดมาม่าไปเยอะมาก
That's really light.
ของที่จริงประมาณ10 โลเอามาม่า10 โล
The sensor is
Yeah,
activated
but-
by light.
มาม่าทุกห้องไปอยู่ที่ห้องเราหมด
A certain amount depending on how much light there's falling on it. Right, so that's brightness, as we call it. And using there, if I'm not mistaken, it's just one strip to radian. So it's just, I can look at it for you.
เท่าไหร่เราจะไปฟันแล้วไปฟันมันได้สิในส่วนที่นั่นไม่มีลดราคาจ่าย
Yeah, so this is all energy here. Well, reflectance is related to breadth. So it's actually the ratio. So there's radiance coming in on the sun, right? And there's the radiance bouncing off the earth, and that's the radiance measured by the sensor. There's radiance going there, and radiance going there. There's the ratio. So not all light is reflected from the earth. Not all light from the sun is reflected by the earth and then reaches the sensor. And the ratio between what's reflected and what's coming in, that's what we call the reflectance. And that's depending on
The ratio.
yeah, so it's the ratio of the radiance in and the radiance out, and that's why you see 1, 0 and 1. So if this is the mirror, everything is reflected, and then you have a high value of 1. If it's really, if your phone is really black or a laptop, then it's 0. If it's perfectly black. So you see if it's very dark pixels have a low reflectance, and very bright pixels like clouds that I'll show you later. They have it's different. They have very high reflectance, so then it's closer to 1. It's a bit more clear. So it's really the ratio. I guess that's the important thing. So it's the portion of energy reflected. No, so that's something you do with the so you do not make you do assumptions. So you make assumptions, you guess what's as a very bright pixel with reflectance near 1. And if you do this reflectance, you can do this per frequency. So you do this for red, you do this for green, you do this for blue. You can also do it for infrared, for instance. All those different frequencies have a different reflectance on different different surfaces actually. So for instance, crops have a different reflectance in near infrared compared to red, and that's something we are going to discuss tomorrow. And that's so the combination of reflectances per band are often enough to classify what's the reflectance is bouncing off. And that's why you say, okay, that's what you call classification, that's what intelligence is about. You say, okay, this pixel is probably road or forest or mice, if you have a very good camera and a lot of bands. So we do this to actually increase the interpretability and the use. As I explained, if you correct it in the right way, you can compare your images over time. And of course, in the ideal world, you would know all the atmospheric conditions at the moment your picture was taken for the entire atmosphere. But we do not know that. We just don't know. There's too much going on. But we do know quite a bit. We have models about how the atmosphere behaves. We have models that are season dependent, and we have models that are just always there. And there are some simple tricks we can do to just not even needing those models. But what's actually happening in the atmosphere? I'd like to show you 3 different types of reflectance that are happening in the atmosphere that are affecting our image. And they're depending on the size of the particles. So, as I said, we have different frequencies, right? So the frequencies have a certain bandwidth, right? So the 1/f. And there are particles that are smaller than our wavelength. That's called Rayleigh scatter. That's for really small particles that are smaller than the wavelength of our signal. For instance, that are smaller than the blue wavelength, smaller than 4 and 5 nanometers. Think about molecules like NO2 or CO2. They are in the air, but they also reflect a little bit, and they scatter a little bit of our of the radiance of the sun. This scatter can either be picked up by the sensor, or it can be scattered away from the sensor. So we think there should actually be more radiance, but it's not there because it's scattered away. Let me see if I compare it. Here. So that would be, for instance, like if here would be like NO2 and CO2, which is there, it scatters off. It's not reaching the sensor, but it's also not reaching the ground. It's just gone. It's actually, if you take this into account, you can take, on average, there will be as much scatter going away as is reaching your sensor. So it's something that's happening, but it's not something we directly correct for, because it's so small. If you look on the other hand at it's called me-scatter. So we think about particles that are similar in size as your wavelength. Think about pollen, dust, smog, right? That is something that does show up in your image. You see it like a haze, for instance. You see smog on satellite images. Why? Because the wavelength is similar size as your particles. The whole wavelength can be absorbed, and you won't measure it. So there is no reflection, and you do not measure it at the sensor. But there are also even larger particles. Think about water droplets in the form of fog, or especially clouds. Clouds are very bad for satellite images in the visual range because they do not, they just reflect everything. There's no signal going through to the surface and reflecting back. So in the worst case, you just have a white image. Especially here in the Netherlands, you've been here for a week, right? You see how much clouds we have. So often in complete seasons, you just have like cloud deck. You do not see fields, you do not see cities, you do not see roads. So that's also something we cannot really correct for, because you do not know what's beneath this information. So what's happening in this? If you look at the wavelength, as I taught you, like the really high wavelengths, short waves, they are absorbed, for instance, by oxygen, so O2, ozone, O3. That's really, absorption is about 100%. So if you go on Earth, you see this light at those wavelengths does not reach Earth, right? So there's 100% absorption. Here on the visible part of the spectrum, so about 400 and 700 nanometers, there is visible light, and there's a lot of this light is reaching the surface. So that can reflect off the Earth and produce a RGB image. So here UV to blue light, so that's actually this part. There are the aerosols, the molecules that are bounced off, so that doesn't reach the Earth, but it does make the sky look blue, right? Because it's the blue light that's reflected. On the other side of the spectrum, there are, for instance, carbon dioxide, CO2. There's water vapor, so there's also part of H2O here that are not reaching the Earth. So you see that if you have sensors that have not only RGB but also higher, longer wavelengths that they are measuring, it doesn't make sense if you want to measure something from the Earth's surface to measure here, because this is reflected by the atmosphere, and we can't correct for it, because it doesn't reach it. So there's, for instance, a sensor would then be located here, and here, and here, and that's the location, that's the information that you can use. So another image to look at this, as I told you, we have this top of atmosphere and bottom of atmosphere. So again, here we have solar radiation coming in. So that's watt per square meter again. It's reflected by the surface, there's reflected by clouds. A part of it is just absorbed, and of course the surface itself is radiating, because where we are living on the Earth is warm. And most of the scattering, as I showed you in the previous plot, is happening in those ultraviolet and blue regions, and then it's better more in the red part of the image. But the blue in an RGB sensor is actually, it measures reflectance. Of course, it's not in this level. So here it's really the absorption of the atmosphere is happening. The blue we are interested in and that we see with our own eyes, that's actually in the part that's not being absorbed, that's really reaching the Earth. So the top of atmosphere radiation is it's not really something that's reflected off the top of the atmosphere, but it's a combination of the top of the atmosphere and the surface. and we want only the surface reflection for our data products. And that's what we correct for. So just one last time, such a nice plot of all those reflectance. You see the direct surface illumination by the sun, that's A, right? We have indirect illumination by the sun because they are scattering, this ray scattering, me scattering, or the water scattering. There can be radiation that does reach the surface, bounces up, especially on waves, for instance, does not reach the sensor because it's going down immediately. And if you look on the other hand, you have the direct path, as we call it. You go from A to D, right? That's the perfect way. You have the indirect path, so that can be again scattered. So that's actually the other side of the P, where you scatter before you reach the surface, here you scatter after you reach the surface. And you have central illumination from the sun, so that's something to take into account. What is that atmospheric correction? It's saying, okay, all this information that reaches the sun, something we do not know exactly, but something happened here, in between this scattering. We measure this, and we want to subtract everything that happened in the atmosphere, and what we keep actually is the information that's happening on the surface. I'll go into those. So we can actually, based on an image level, we can subtract what we call dark objects, and why I'll explain. You can do a slightly more difficult version where you also take into account the solar zenith angle, so that's the elevation of the sun, like we discussed, the theta. But you can also really do it on a pixel level where you say, okay, on this pixel the atmosphere consists of this amount of oxygen, this amount of NO2, and you take all that into account. And you can simplify that a little bit, that's called SMAC, Simplified Model for Atmospheric Correction. It's a really brilliant acronym. So dark object subtraction, this is the one we in practice, and I think most of companies and scientists use, because it's doing a good enough job. And that's something to take into account, and Mark's already nodding because he knows what I'm talking about. You can make it very complex, and I'll show you how to do it just a little bit. But in the end, you can assume that you have your image, and there are certain parts of your image that are dark, right? That can be a sea or a dark field, or at least some pixels are on the dark side. It's just not Star Wars, but they are like really on the lower end of your histogram spectrum, so they have low reflection. What we do then is that we actually say, okay, this dark object, it's not perfectly dark, right? There is some reflection. We say, okay, that reflection, we subtract that from the entire image, because this object should be dark, there should be no reflectance, but there is reflectance, and every reflectance that's present at that point is due to the atmosphere. That's it. So we say, okay, we measure, it shouldn't reflect anything here, right? This is dark, this is a black hole, but some information is reaching it. At that point, we know that everything that's reaching our sensor has gone through the atmosphere. It increased somehow the reflection, and that's it. We subtract that from every pixel. We just take it thereby into account, for instance, at that location, the sun angle, the water vapor that's at that moment of taking the picture into account, and you just subtract that. There is, of course, a drawback. You do this for one image, you have to do this for every new image you get. You cannot say, okay, I took an image last month, and my darkest pixel had a value of 50 out of 255, and I took an image today, and I just subtract 50. Now the conditions changed, and that's why it's so powerful, because you just look at the dark object, the same dark object probably, and you see, hey, it's not 50 today, so the atmospheric correction is not 50, but it's 30. There are different conditions. The sun angle is different, the aerosol concentration is different, the water vapor is different, there are less clouds maybe as well. So I just subtract 30 from the whole image. And that actually is often enough to compare time series of images. So this is probably the one that you're going to use most. Yeah, so what we call the path radiance, that's the one going from the sun to the earth directly back to the sun. And so, toward the center. That's then subtracted from each pixel. And as I said, so they are not really physically based corrections, but they're good enough. If we look at the cost, it's a cost method. So this is the DOS, the DOS. Cost stands for cosine theta. And theta is the solar zenith angle, so you take into account the solar angle, and it's a bit more precise. So here you see the cosine of the theta. Actually, this is probably a DOS variation. I'll look at it up and correct it for tomorrow. And it's an extra way to correct, at least like the one I showed you at the radiometric correction, to take into account this distance of the sun to the earth and the angle we're using. And it's slightly better, but it's also slightly more difficult, because you have to look up the sun angle. And with this, you do not even have to look up the sun angle. You just take all the information from the pixel. So actually what you do is you stretch your image and you say, okay, this is my image. It looks like this in practice. I hope that's a bit clear. It's a rather fake image. I've just seen images of the gecko that are much better than this. But you say, okay, this is my dark region, right? This should be 0. I'll take an average over this area, and I say, okay, everything that's in there is affected by the atmosphere. I subtract that value from my entire image, and especially here, this region, you see that there's a better contrast. Alright, that's the power of it. So in general, the contrast increases a little bit. Why that is, I'll show you in a few slides where we really are going to look into histogram stretching. Is that a term you've heard before? Maybe a little bit. I'll explain it, but that's actually what's going on here. If we look at the more difficult versions, so we have what we call radiative transfer models. So that's really something where you assume that at the location where you took your picture, there's a column of air going all the way from 0 up to your spacecraft, right? And you assume that there are certain amounts of molecules and certain amounts of, for instance here, we have ozone and we have certain temperature, and this is altitude, so we have from 0 to the top of the atmosphere, 100 kilometers. And we also say, okay, it's changing between summer and winter. You have different spectra. So this is the difficult version, because we have to know information about ozone, about aerosols, about water vapor, and especially for the 6S model, you need to know them all in very much detail. What you get is a corrected pixel, which is probably the closest you can get to a physical quantity of what that means, what's present at the pixel. You correct it the best because you subtract everything. But remember, you're still using models, because we do not know exactly what's going on at the moment you took your image. You just assume, okay, it's like today it's 3rd of July, it's about midsummer, right? So we assume this model, we correct our image all the way for all those different latitudes, and at the latitude and longitude you took your image, you correct it for all different heights, what's going on for the ozone and the temperature, and then we get a pixel value. So you really calculate this per pixel. It's taking hours as well. It's not something probably you want. You actually do for this simplified model of atmospheric correction, the SMAC version, it's taking into account a bit less detail. So you do not have this model, for instance, per pixel, but for, let's say, 50 by 50 kilometers or anything you want. And then still you recalculate all the pixel information. Sometimes this is implemented in, for instance, the information the European Union satellites, the Sentinel satellites, they correct it for this sometimes. You can download the 1C level ones that are not atmospherically corrected, and you do it yourself, or you can use the 2A level. then I guess they have their own version, because we tried to mimic it and we haven't yet managed to do it. But they have their own function of all those different types of models, and they correct it. And say this is the best. What we do in practice, we just take the 1C images, we do the dark object subtraction. Sometimes it costs, if you really know, if you want to compare, for instance, an image every month, you can take into account seasonal effects, and you do that better by taking the sun angle into account. But actually the sun angle is already part of the DOS. So yeah, I would say keep that in mind. But this is also very important. Some atmospheric effects you just cannot fix, right? As I told you, if you have dense clouds, you are not going to measure anything beneath it. Then you need radar. Because radar is penetrating clouds and then bouncing off the earth and bouncing back. Then you know something. So radar is best if you have very cloud dense regions, but radar is not giving you all the spectral photons. There is nothing at certain wavelengths. It's radar. It's just you look at the reflection. Smoke is another one. So if smoke is very dense, so if you think about fog or things like that, or haze, you cannot look through it. And the same is for shadows. That's something that's a bit difficult. So clouds project shadows on the ground because you're at a certain elevation angle, right? It's the same with the mountain. You're not perfectly on top of the cloud, but you measure at a certain angle. The sun is at a certain angle with respect to the cloud, so the cloud is dropping shadows. The information in the shadow is affected by the shadow because the radiance there is different. There's less light reflected because you're in the shadow. And then the information that is in there, you already see it in the color, it's of course darker. If you just look at RGB, it's darker. If you look at infrared, for instance, and you calculate the vegetation health, something we're going to tomorrow, it will be affected by the shadows. And we do not know how to correct for that. Or Mark, do you know anything about correcting for shadows? No, too bad. So not yet. Yeah. This is what I wanted to tell you about the corrections. So we have all those different types of corrections where some are more difficult than others, but this is actually this is the most important, where you just look at the image itself, you use the information that's in your current image, and then extract the average there. So I want to, we actually discussed this a little bit, and I'll go into it a little bit. We discussed image rotation right the morning with the resampling. You can of course zoom in, zoom out, but you can also say, okay, I want to upsample or downsample it. That's something that sometimes is useful. So, for instance, like we discussed with the digital elevation model, if you have a different resolution, you want to bring them together at the same resolution. So let's say we have information that's, we have satellite information, you have a 50-meter resolution, right? And you have an aerial photograph and it's 5-meter resolution, so 10 times as good. What you can do is then just what we call upsample your 50-meter resolution, and you just, I'm going to draw again, let me see, I can do it here. So we assume a perfect world again, so this is my sensor, this is 50 meters, like this, it's a satellite, and we have a photograph or a drone image, and it's like 5 meters. Well, this is probably 10 in my drawing style. What you then can do is just virtually say, okay, my 50-meter pixel, actually, if this is 10 by 10, then that's 5 pixels here and 5 pixels of our higher resolution data there. So you say, okay, my 1 pixel is actually 25 pixels. And we give them all the same value. And then that's what we call upsampling. So you increase the it's not really that you increase your resolution, but you increase the resolution you can calculate with. So you make certain that all those matrices are aligned. There are ways, end of my presentation I go into pen sharpening, where you actually use information from one satellite, where you can increase the resolution of your color bands. We'll wait for that a little bit. Alright, just some terms, because sometimes you don't need the whole image, right? If you have a certain region you're interested in, this is your entire image, you're only interested in the lake and its surroundings, you clip it. That's what we call clipping or subsetting. Why? Well, it saves disk space, right? It's a very simple reason, but it's often also saving processing time. If you're only interested in that, then that's good. Keep in mind, as we refer back, for the dark object subtraction, you do that on this image. If you would do your dark object subtraction here and your dark object would not be in the image, then you get very strange results. So if this would be the region you're interested in, and this is your dark object, you first do your correction, your atmospheric correction on the entire image, then you clip it, and then you analyze it. So if you would take the darkest pixel from this region, that's a different dark pixel, maybe not even dark, but in the overall image it's like somewhere mid-range, and then it's not working anymore.
I have a question.
Yeah.
So normally every image gonna have dark pixel.
Yeah, that's a very good question. That's something you assume. So if your image is large enough, then it often works. Yeah. What sometimes works, and that's also part of this one, if you mosaic it, so that's combining multiple images in one. If you so here you see this is an image, that's an image, that's an image, and that's an image. You have this line here, right? If you balance the contrast and the color, and we'll look into that later, you get one image. You can minimize, of course, the boundaries by, for instance, averaging again the pixels that are on the boundaries, filter it like we did for the black stripes. Then you get one image. If you look into images that are taken almost at the same time, so your satellite is flying overhead, and you take some images that are taken one after the other, you merge them, you get a larger region where a dark object is more certain. Yeah, there's a higher chance of a dark object. So that's one of the ways to do it. So contrast, that's as Ted said, if you want to upgrade the image, so sometimes it's a bit blurry or sometimes it's not so sharp, you can increase the contrast. So we actually alter the relation between the pixels. This is a very vague sentence, but I'll show you what it is. But we do not alter the image itself. We are not we're not blurring it or we're not enhancing it. So we're not giving different values and not relations between the pixels. But we do stretch the histogram, and this is better explained by an image which is on the next slide. With spatial filtering, we are actually changing the values, like we did with resampling, because we are smoothing it or sharpening it. We can use it for edge detection, then we're actually really changing our image. This is actually contrast modification. If you look already at those two pictures, then this is much more clear than that one, right? So it is much better contrast. What we do is actually, this is the original, so this is grayscale, it's just one band. You can do that for any band you have. You see that there's values between 0 and 255, right? So 8 bits. This is the original histogram. It's very small, and it's almost all on the darker side of the image. That's here. You see it's really dark. What you now can do is apply a transfer function. That's this one. You say, okay, a value that's here at, let's say, 30 should be here at 60. So you stretch it, and that affects something you see here. So instead of only taking into in the range of the dark values between 0 and 50, it's now, this has a slope of 2, so it's now between 0 and 100. So you say, okay, the dark pixel here at 50 is now a much lighter pixel at 100, and then you see contrast. Because contrast is nothing else than the distance between dark and light colors. And if you stretch that, then you see it much better. What's important here is the slope here. So here, as I said, this has a slope of 2. So here at 50 we are at 100, and here at 100 we are at 200, right? Beware, if you make the slope, if you think, okay, this is not good enough, I want to have stretch much more, I want to increase the contrast, I'll make the slope at 5, for instance, then it's so steep that already the pixel, for instance, a pixel at 60, and you stretch it with 5, would be at 300. But there is no 300 in an 8-bit image, right? So you have, that's another version of, that you clip it, you just lose information there. So this will be very bright, and there will be a lot of contrast, but you will have lost the pixels that were the brightest in your original image. Does it make sense? Yeah, right? Cool. So that's a way to increase contrast. This is a good example also to explain dark object subtraction. You would assume that this peak, right, you see the smaller peak, is your dark object, right? That's the value of it. So you say, okay, this pixel has a value of 12, something like that. That's the lowest value, that's my darkest object. So you subtract from all those values, you subtract 12 in that band, for every band. So it shifts a little bit that way, but you lose then the atmosphere influences. After that, you of course again have to stretch it to get a bit more contrast, and the best way sometimes even to do that is to do what we call histogram equalization. This is again the change from that image to that image. This is what you want, right? Here you really see mountains, you see a lake. What we do is, in theory, what you want is you want to produce a flat histogram. So this, in theory, would be a flat line. In practice, you can't transform this histogram to a flat one. But you can get close. You can at least get closer, right? That's what you see here. So you see that pixels are actually from, this is actually the same amount of different types of pixels, but they're now just stretched out over the entire range. So sometimes even what we call, this is actually what we also call histogram stretching, and that really is a good term, I think, for it. Because you take your histogram and you stretch it all the way to the entire range of information that your image can show. Sometimes you can overstretch it. Not that you have clipping, so it does fit into it, but that, for instance, that some dark, if you have a dark region, a forest, for instance, where the maximum pixel just should be like 150, but you overstretch it, you get a too light image, right? Then you and I are thinking, wait, what's wrong? This is too bright. But that's because you overstretched. So that's something you can tweak a little bit, and that's something we can do visually. Just to say, okay, my image should look a bit like this. I want to look it like this. That's how much I stretch. And then you stop. But that's also where we finish today is the visual interpretation. That's where that's then what you help, because you enhance the pixel. This is difficult to interpret visually. This is much better. You see the mountain ranges, and then you say, okay, that's good enough. So sometimes you have, like I said before, you have random noise or speckle in the data, right? So you just have some random dots. You want to filter it. So this can be a kernel. Is convolution a good term that you are familiar with? So convolution is, the concept is pretty simple. If you have a matrix, that matrix, you take that matrix and you say, okay, I'll start in this region of 3 by 3 pixels, right? 9 pixels, that's also 9 pixels. What we do is we take 1/9 the value that's in the top left, 1/9 the value that's here, and we do that for all 9 pixels, and that value we say it should be in the middle. That's what we call filtering, smoothing in this sense, because what we do is, okay, we say if this is a very high value and it's a bit lower, and there's a difference, so you see here a very sharp edge, right? So you see this is low, a low value, high value, low value. If we take the average of 9 pixels, 3 by 3, then that will be somewhere in the middle. It will be not too high, but it will also not be too low. And that's what we put back there. And if you apply that to an entire image, and that's what we call convolution, because you do this for each pixel. So you have this 3 by 3 matrix, you begin here, the next step would be to put it here. You calculate that pixel, and you what we call convolute this one, you go just row by row by row over your entire image. That's how the computer is doing it in the back. And in that way you calculate a value for each pixel in the image. And you get a new value. And there are different, what's interesting that there are different ways to put values on this. So this is what we call a weight. So here if you take 9 pixels, you have 1/9. So each pixel is as important as the other ones. But if you take different values there, for instance, here this is what we call sharpening. Look, something's changed. We say, okay, this is still 1/9, but it's negative. We say, we make it less important. We want to have this value actually much more pronounced. Let's say like twice as in the total surrounding it, 17/9. So still this would be 1. If you sum all of those values, then you still have 1. So the kernel has a total of 1. But if you apply this in the same way, what we do is sharpen the image. So now, if you have a value that's low and it's high and it's low again, this value is, if this would be low, high, low, this value you would multiply by a positive value and you would increase the value. So you would sharpen it. You would have the high values stand out more compared to the low ones. Where is that applicable on satellite images? Mountains. Right? You really see the edges. And that's what we call sharpening. So you increase the contrast. What does happen, of course, if you have noise, you will also increase your noise. So if you have a pixel with noise, you multiply it by 2, right? Almost 2. Your noise will be popping out more. So that's the trade-off. You have to choose what you want to see. If you want to see a smoother image with less noise, or you want to increase the contrast and sharpen your edges. And that's something you can just play around with. Alright, I have a few more examples. This is cool. Edge detection. So sometimes you can emphasize edges. So this is I have 2 examples here. So you can have, for instance, one where you say, okay, I just look at the edge like this. So we have -4 here, and we subtract the ones there. Or you can do, for instance, 2 in the middle, so make it actually the other way around. So here you subtract your middle value, and here you add it. So that's the other way. What you do because of this direction, right? There's not really, you take information into account from above, below, left, and right pixel. That's what we call isotropic edge detection. You take into account information from any direction. You can also do it, as shown in the next slide, by just taking, for instance, a certain direction. If you do this, you see that the edges are standing out. So here you see that the edge, so that the transition from low to high, it doesn't matter if you go back to low again. It's just to transform the step from low to high. That's where this gives a high value. Because if you go from 0 to 100 in 1 pixel, this kernel will make it stand out. And you can make it like a positive step or a negative step. That's why here switched. And you can have different weights, so you can actually choose if you want to have a large step highlighted or already small steps. And that's something you can just play around it again. Here again you see this direction, right? That's something you see here as the edge. So the edge will be you have high values and the rest is lower. Where is this of interest? Well, for instance, if you want to detect roads, for instance, or something that's going horizontal or vertical in your image, or diagonal, you can use what we call Sobel filtering. So those are the kernels. You see, hey, the middle here is 0. So what this is actually detecting is vertical lines. You subtract the one on the left, and you add the one on the right, and you do not take into account the middle. You will detect the stripes. You can also do this horizontal or diagonal in that way, or diagonal in that way. And in that way you actually highlight features of your image. So here, I have to look up which one they applied here, but if I'm looking at it, it seems a bit like the diagonal one. So you see that those lines are highlighted, while those are less highlighted. So here on the X of the lake, this direction is more highlighted than that one. Why is that of interest? Well, maybe there are certain features that have really sharp edges that you want to detect. I'll show you an example tomorrow where I detected every zebra crossing, like the stripe patterns, in this province of South Holland using this technique. So there you really need to detect those edges. Alright, we're almost finished with pre-processing. This is one technique I would like to mention, not go into too much detail, is pen sharpening. So some cameras, not the Gecko, but there are a lot of ones, and SCS is actually, I guess, producing ones with bands. It's what we call pengrammatic. Pengrammatic band is not measuring the radiance in one small frequency band, it's measuring the radiance in a large band, so spanning often the R and the G and the B, so the red, the blue and the green regions of the spectrum. So it's getting in a lot of light into it. Think about the camera and think about the shutter time. So the more lights coming in, the less shutter time you need, or the higher the resolution can be. And that's the case here. So pengrammatic, they're actually 0 to 255, so they're just one band. So you can see them as black and white or grayscale, but it's meaning pengrammatic, all colors. They stretch over broad frequency range, and if you combine that with information from the RGB bands, for instance at lower resolution, for instance the pen band can be, this is an example from a website, which is 60 centimeters pen band, really high resolution. RGB, it's still very high resolution, 2.4 meters, but you can increase it. But this is 4 times as bad as that one, but if you align it and calculate the effect, actually scale this pixel by the value in the pen band, you get this image. And this is a clear improvement, right? So you really get more information. What's important here is that the relationship between the spectrum the pen band is measuring and your RGB sensor is taken into account. So sometimes the pen band is just measuring half of your red band. Maybe draw that a little bit. So if you have your spectrum again, right, from blue, green, and red. So this is the sensitivity of your sensor, right? Your pen band might do something like this. Oh, it's not so sharp, of course, a bit like this. So you see that information within the pen band has completely all the information that's in the green band, but not this part from the blue band, and also not this part from the red band. That's something you have to take into account, and there are different algorithms for that to look into it, and software packages that take that into account. We're almost done. I'll just like to show you how you can look at images, because this is like we have pre-processing done. We know the steps to go from this quite dark image with less contrast to this image with much more contrast, which is corrected for the atmosphere. But now what? You can look at it because we are interested in the information, right? And then we have to look into different type of information about how we process visually those images. And there are some basic elements and a certain ordering of what we look at. Of course, an image, an RGB image has color, right? It's what we call tone or color. It's very primary. It's the base. It's the element your pixels are made up of, RGB. If you go one step below that, you can look at sizes of objects that you see, or shapes of objects, or texture. we can even go one step further. You can look at patterns of objects with a certain size, or patterns of objects with a certain shape. So if you see a lot of circles and you know it's agriculture, you're pretty sure it's pin-based irrigation, right? Where you actually have rotating irrigation. You can look at height. You can look at shadow. There's a combination of those. So if you're really high resolution, we sometimes use shadows to determine height of a building, because you know the sun angle, and you know the length, and you know the time of day, you know the length of the shadow. You can calculate the height. It's the third step. You can go even higher and say, okay, hey, this is a certain site. This is a industrial complex. So these large buildings should be factories. It's not a living house. Or you go in city center and say, okay, this is a park. This is not a forest. It's just a park, and this is a small river. It's not a river going to an ocean. So you can make associations, and this is very important for your intelligence work. So this is the slide with the most text. This is for you to read at home. This is actually what I explained. What I just explained to you. So we start at tone and color, so there are variations in color. Those are the basis for things like shape. So if there are certain pixels with the same value next to each other, we as humans see shape. And tomorrow I'll show you how we can teach the computer to also see shapes there. And then we can also look at texture and patterns. You can look at irregular shapes, you can look at man-made shapes. So man-made shapes are often pretty sharp. Look at this building, it has nice 90 degrees corners. Nature doesn't make 90 degrees corners. Most often not. And all those things. An association is also very interesting indeed. If you have a residential area, or if you have an industrial area, or lakes, you can make associations. So sometimes some things are, if you see something in a lake, it's probably not a house, right? It's rather a boat. And those kind of associations, although I know in Delft a place where you can live on a lake, but often not. So if you look at the image, here you can see a little bit of it. So you see tone, right? This is bluish, greenish. This is dark. So there's a difference in color. So that's already telling me, okay, this might be bare soil with trees. You can look at shapes. Oh, this is a rectangle. It's not natural, probably. It's probably a house. You can look at patterns. Okay, I see rows of trees, or I see rows of buildings. You can look at texture. So you say, okay, there are similar colors, but they are slightly differently oriented, arranged within a certain object. So it's probably the texture of a tree. And maybe even if you have very high resolution, if you have drone images, I have drone images which are 0.9 centimeter resolution. You can see the nerves of the leaf. You can actually determine what kind of tree it is from the leaves. Shadow, as I told you, you can determine height. And this is a road, and there's trees here. There's an industrial complex. What does it tell me about where we are, for instance? So that's my story for today. I just have some very nice images where I would like to challenge you to tell me what do you see, just as a practice. Hey, it's 12 o'clock, it's almost lunchtime. This is a Sentinel-2 image. It's pre-processed, of course. This is not how we downloaded it. This is something we did ourselves at Fujitsu Impact. We enhanced the image, right? We stretched the histograms, we corrected it using our object subtraction. And we see a very nice region in India. This is near the Himalayas starting. What do we see? It's a river, yeah. Is there something special in the river?
Dam.
A dam. Hey, that's interesting, right? Because this is something you really see already on the Gecko images. It's really cool.
I have them here, by the way.
You have them here, yeah.
Yeah.
I'll show them after this. Anything else? Fields, right? Neatly arranged fields, I can say, right? They're really cultivated. You see, this is human-made. They're straight angles. Somehow we do that as humans. There's a lot of forests. Yeah. Here, this is a city, so my association would be there. There are people. let's see. We have some highlights here. This is, for instance, you can monitor urban development, right? Is your city growing or shrinking? Are there illegal settlements somewhere? You can monitor the water quality here before your dam, or you can see what the height of your reservoir is, and then calculate the storage volume that you have in your reservoirs. You can look into how your crops are developing. Right, other example. This is in Dubai. You do recognize some things. There's indeed, this is probably an airport. Yeah. We do see the city, I guess. Indeed. Yeah, this is pivot irrigation, right? It's agriculture, so it's circular. You actually see the stripe of the irrigation pivot. You see, of course, the roads are very clear. It's all desert. I have some examples.
I was actually asked earlier what those round things are. Because I think in Thailand they don't have that kind of irrigation.
In Netherlands we don't. I actually learned about it from doing work in the US.
Yes.
So what's it is that actually, if this would be your field, it can be very large. There's in the center, there's a irrigation bar moving around, and we call it pivoting. So you pivot around the center, and it's actually irrigating the field in a circular way, and that's why you have all those circles. So in Holland as well, maybe also in Thailand, we have more like this, with all the fields next to each other, and then maybe some water in between it. So here, that's actually we have the agriculture. This is also interesting. So of course, those are regions where there's a lot of coastal information going on, coastal development. So also here in Holland, like 20 kilometers away in the sea, we had something we call a sand motor. So we put a lot of sand in the water, and we let the North Sea move the sand towards the beaches and grow the beaches again. Right? Yeah, some brilliant Dutch idea maybe. I don't know. It did work actually. So we have now very nice new beach, and we have enforced dunes. So the dunes grew from the sand we put into the water. If you would do that here, you can monitor how the sand is moving over time, because it took like 3 years. You're not going to install a camera and look at that. You just say, hey, give me a satellite image every month and show me the time series and how it's moving. That's why we use satellite images. So I guess this is probably the last one I have. This is Namibia. This is a bit processed, but it's so why is it blue? Because the radiance is so high, and we stretch the blue band a little bit. But you see how sharp your information can be, right? So this is the top of a dune. So here, really, the sun angle is important. So the sun, you see that there's shadow that way, so we know the sun is on that side. You see here the roads. Anything else that's really getting your attention? There's a lot. The roads are really clear. Because I've actually been here myself, and this is really desert. I can't hear. If you look, we have this one in our office, and you look at it, you see the tree. I can't. Sorry.
Blue color.
Yeah, the blue color is because we stretch the image because it's really light. So this is very bright. So there's a lot of reflectance in all three bands, but mostly the blue because I guess it's due to the sand. So this is very red sand. It's called the red dunes, and this is very light colored sand. So we stretch the histograms like I showed you to get the blue and the red a little bit out. But there's no green here, so that's also where your image is, because nothing is growing here. It's all empty. So what do we actually see here? Let's see. You see the roads. You can look. This is pretty high mountains. You can look at geology or minerals there. You can look at the dunes. I have some images here. Maybe you can show them.
Yeah, I showed some of them before, but maybe now in the same line you can just go to the folders that says Gecko processed, I think, and just maybe directly after this. While you're doing it, Firstly, one of you asked me on the very first day, I think it was you who asked me where the source was for that image of the applications. I found the source. It was a presentation that was held in 2014, and there's a conference proceedings. I'm putting it in the PDF, and I'm updating the PDFs, and I will give all my slides to Hong Yang, and he can then give you the updated version. Most of them are the same, but here and there I fixed a few things. So just overwrite the old ones you have with the new ones. And another thing I wanted to say, which I thought about, is you asked a lot about how will images from a 5-meter resolution camera look. Now there's a very good source for this. It's not our images, but Planet Labs, which the company Planet Labs, they now changed their name to be Planet, but they have a website called the Planet Beta Explorer, and you can access this for free. You just need to register first, but it doesn't cost anything. And they have the whole world, like Google Maps, and you can zoom into any place in the world and look at it in 5-meter resolution. And it has a slider at the bottom that you can choose the date, and they have every month. And for every place on the world, they have monthly images for any place. So you can go to Bangkok and look at Bangkok at 5-meter resolution from their satellites. Now, of course, if we build you an imager, it might be better than their imager actually, because their imagers generally only have red, green, and blue, also with a Bayer pattern sensor. No, they do line scan, I think. But images that we build can, for example, have specific bands like near infrared, or it can have a pan band, or it can have any other specific bands like the Worldview 2 bands that might be interesting. Because if you build a 5-meter satellite and it's RGB, the best you can hope for is to have what they have, but you can get that data for free anyway. So if the data is the part that is important for you, I don't see why you need to have your own satellite. You could just download it from the internet or from Planet. But of course, if you have your own satellite, you can put features on it that is specific to your needs. So Google Planet Beta Explorer, and you will find it, and it will give you lots and lots and lots of useful data about how 5-meter looks. Thanks.
Thank you.
Yeah, so this is actually more like the images you will get after some histogram stretching, I think. It's interesting to see already which features you can see, right? So you see the road very clearly. You can see the lakes, for instance. You can see agricultural fields here. You see the clouds and the shadows, of course. That's not something we as a data processor or as a sensor deliverer can do anything about. Is it cloudy actually in Thailand? Yeah, right. So that's something to take into account. This is here you see the comparison with the image I just showed you. This is the 30-meter resolution. You very clearly see the fields. And you see the lake. You can actually see the water dynamics in the lakes. So you can see the roads. You can see the mountainous terrain. And here you see maybe you need some correction. So this might be a bit elongated. If this would be a perfect circle, then indeed the DEM can. This is a little bit stretched. Then if you do this auto rectification, you can do it a little bit better. You see, it's not that necessary. Actually, atmospheric correction is most important to get this type of images. I guess, François, this is stitched or?
Yes, so these are two matrix images that I stitched together. So you can see the satellite was sort of traveling in a diagonal direction compared to the orientation of the imager. And this is also a dam in South Africa.
The famous one. It's empty reservoir.
This is not a famous one.
Oh, okay.
No, this is just a dam, but it's not a famous dam.
So here you need two images to get the whole reservoir. So that's the mosaicing, or sometimes we call it stitching. So you really stitch them together. Here you see a little bit of an effect of the transition probably between, but it's very small. So actually, if you just look at this, do your visual interpretation. It's a really good image actually.
Yeah, so this satellite is a 2U satellite. It's a very small one, and because it's only 2U, we couldn't really put a complex attitude control system inside it because there was not enough space. So this satellite only has one reaction wheel, and it has been programmed to always look down to the ground beneath it, or try to point down to nadir. So there's not a lot of geometric distortion on these images because mostly it's looking straight down.
Yeah.
The disadvantage is that you only can take pictures of parts of the Earth that go directly underneath you, and if you're flying 20 kilometers to this side, you're missing it, and you could have tilted the satellite to look there, but on this satellite we didn't have the capability to do it. You will now have a much larger satellite with a much better control system, so you can actually point it in directions that are interesting to you.
Yeah.
Yeah.
Two more. This is very good for river monitoring.
So those are 3 images that were stitched together.
Yeah.
This one, yeah.
So you see there's a lot of overlap, right? Also here, I guess in your squad. So you see here there's images, and then you can just, what we call, do image-to-image mapping, and say, okay, this part of the image, so this is one image, this is the second image, this is the third image, they have overlap. Then you can, for instance, do this using your ground control points. You can already stitch them together very well, and then you only have to do for the complete image located on Earth. But stitching is much easier if you can do image-to-image mapping.
Yeah, to give an example on this one, because the ground resolution on this satellite, because it was flying lower, was 30 meters. So each rectangular image is about 60 kilometers by 30 kilometers, roughly. And you know the satellite is moving across the Earth at about 7 kilometers per second, but the height of the image is 30 kilometers. So you have a few seconds you can take an image every 2 seconds, for example, and they will overlap by quite a lot. And it's not difficult to take every 2 seconds. An imager can take at 5 frames per second. So you can really have very big overlap, but that's too much. You can wait 2 seconds, 2 seconds, 2 seconds. You can even wait 3 seconds, but if you wait too much and the overlap becomes very little, and maybe the satellite isn't very stable and it is rotating while it is taking the image, then you start to have challenges.
Yeah, it's always better to have some overlap. Yeah. Let's see, we have one more example, I guess, from you. Nice coastlines.
There's a ship in the image. Find the ship.
And you see the clouds, right? So that's something, and this is hazy, so sometimes you see there are ways to correct for the haze. That was too advanced for today. But you see, like, there's some information here. Here there's no information of the Earth, because it's really cloudy. But here it's partly clouded, and then you can, again, average things, for instance, and then and remove that. Well, here you see, right, how bright white this is. So that's with clouds. So often with clouds, actually the last thing I'm going to say today, we often work with images with clouds. You download your image, you get your image, for instance, from Planet, we buy images, and you think, oh man, it doesn't look good, right? So you have clouds very bright, and then the rest is just almost black. That's where your histogram stretching is important, because then you're going to stretch all those bands and increase the brightness. And then you finally see, hey, wait, the clouds are white. I mean, you can clip clouds. There's no worry about that, because there's no information. But then the contrast between the fields, for instance, becomes much brighter, and that's something you can use there. So that's something you're gonna experience. Sure. Well, this is good time. So Young is there to. I guess to take you away from me. I'm finished.
Okay, alright, now the next time.
It was my last image from Vosma.
Yeah, I was checking because the pizzas are already there. I haven't seen the bus, I think, yet. That one is coming, but maybe you can already bring up the pizzas that you
Nice. What are your plans in the afternoon? Shopping.
I'll take
cool.
Yeah? Okay.
Then it's good to
Well, then
yeah, I have some questions, resources tomorrow in the afternoon. I've used 5 books for this. There's also information online. There are some free books and some you can buy, and they're really good. So that's good. We can look at the size of those clusters, shadows to determine, for instance, height. We have texture, so there was more like the combination of the different colors together. The pattern is more a combination of shapes. So how are shapes organized? Is it something like a block of houses, or is it the lane with trees, or is it the harbor with ships? That's all patterns. And on top of that, we have the site or the association you have with certain locations, like a park has trees and then maybe a lake, a harbor has boats and marina and some buildings. Industrial complexes have different buildings than urban areas. Farm fields have different associations than cities. So you can basically think about it as you interpret those images and as you present them also to your audience or your clients or your bosses, of course. So that's what we discussed yesterday, very quickly. Yesterday in 5 minutes, it took us 2.5 hours yesterday. So today it's more about the analysis. We have this image, we visually inspected it, we have looked at it, we think it's correct. So what can we do then? So our program of today, it's actually, well, we have lunch around 12, I understood. We of course have a coffee break in between. We start at around 1 and I think we'll be finished at about 3:30, depending on how much we discuss and how many questions you have. I have the time, so that's fine. We start today with some different types of data. Are there people here who are familiar with the geographic information systems and the types of data? Some are. So then we're going to discuss the raster data and vector data, and maybe those are familiar terms. Then we're going to look at how to classify our raster data using several algorithms, supervised and unsupervised. We're going to check how to combine a lot of images over time. So can you detect change, which is important for your application, I think. And we look very quickly in a more technical way at combining images over scale, so different sources of information, how can you combine them. And the whole afternoon is filled with applications, a lot of applications. And at the end of the day, I'll also discuss a little bit of software that you can use for analyzing this data, that you can either program yourself or that's a software package that you can use. So let's start with the content of today. So this is really a bit of the GIS start. So this is vector data is something else than the images. So this is not something the satellite is providing you, but it's a way of representing information on in a geographical way, so to say. So you can have points, and a point can be a coordinate, right? So it can have a latitude, a longitude, or on a map an X and Y component. So it can be used to say, okay, this point on our raster is meaning a church, or it's indicating a mine, right? That can be done with points. If you combine points and you have X's in between them, and they're implicit, so you define only the points and you say, hey, it's a line. So you say, okay, I have 3 points, and that means if it's a line, that there is a line. Just like this, from the first to the second, from the second to the third. This is a way to, for instance, represent roads. So for that, you do not have to have like a pixel and a pixel and a pixel and a pixel. You can do that. But you can also say, okay, I have pixel, 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 pixel. And that way, I'm gonna translate this to a line, which is much quicker to analyze and much simpler to store, because you only have 3 points instead of maybe 20 pixels, right? The third version is a polygon. This is a rather difficult polygon, because you can have points, you have the coordinates of the points, and you see that there's again a line in between. The difference between that one and that one, can anybody guess what's the difference? It's closed, huh? Yeah, that's the whole idea. If I would draw a line here, then it would be a polygon. So if I have 3 coordinates and I specify it's a line, there will be 2 segments. If I have the same coordinates, but I say it's a polygon, I will have 3 segments and it will be closed. So that's a very important distinction. Why would we use polygons? For instance, you have your clusters. You have detected a certain cluster with a shape, with a size, and you say, okay, it's like 20 pixels again, or 40 or 50, but I only want to have the boundaries. Then you can draw a polygon around it, And there are ways to do that automatically, and you can store the information as a polygon. And that's something that you then can, for instance, use. Also, if you do that over time, you can have changes in your polygons, and you can do analysis on those polygons. You can also, of course, compound them. So you can have in one file, for instance, you can have multiple polygons, so more than one. There can be holes in it, so you can have like a donut shape with a circle, the outer circle and the inner circle, so it's more like a ring. You can have lines that cross, and there are several types of calculations you can do. For instance, here we see buffering. So we have a line, right? Let's say this is a river. And you want to know what's in your satellite image within 5 kilometers of your river, on both sides of the river. Then you say, okay, I have this polygon, I create a buffer, which is very easily done in software. You say, okay, I buffer 5 kilometers, and I'll take all my pixels within that region. Then you don't have to analyze the whole image, like we discussed yesterday, but you can only analyze those pixels and say, okay, how high is my water? Are there indications of flooding? Are there indications of drought? Because my water is actually declined. You can also do that on different regions. So you can say, okay, maybe I'm more interested in the forest within 50 kilometers of my river, and see what the impact is of drought in the river on forest within this buffer. Then you can create a buffer which is larger. So that's a certain type of what we call spatial analysis. What you can also do, especially on polygons, is that you can check if they overlap. You can check, so that's intersection. You can combine them. So if you say, okay, I have a lot of polygons per house, but I want my city, then you just say, okay, union all my polygons, and they're one polygon. And then you can use that, for instance, that one polygon, you use it as a mask. So you put it on top of your satellite image and say, okay, get me all the information that's from the houses or from the city. And you can do different, for instance, let's make a good example. You have a forest, and you have another forest, and you want to have, let's say, a forest with certain trees, with oaks and with pines, right? And there's a region that has both of those type of trees, according to your GIS department. So you have probably in your intelligence department, there are people working with geospatial data. Say, okay, here that's this type of forest, and that's this type of forest. Sometimes there's overlap. But for your analysis, as we will see in the next slides, you maybe want to have only the forest that contains oaks, because that's your class that you're interested in. Or you want the forest that has only pines. Then you can do the difference and only take from the green part, only take this first, this part of the polygon, create a new polygon from that, and use that as a mask. And in that way, as I already said, so you can actually use it to clip or cut out parts of your rasters that are of interest to you. But also in the software I'll show you this afternoon, like Quantum GIS or ArcGIS, you can use them as overlays. So you have your satellite image as a base map. Think about Google Maps, you put it on the back as a background, and you put all your rasters on top of it, and use that in your interpretation. So how is this stored? Well, the easy ones are GeoJSON. Are you familiar with the JSON format? It's called JavaScript Object Notation. It's a very simple text-based method. So you have like in HTML, you have like you have brackets, and you say, okay, my name is forest, and you close it with another name tag, and you say coordinates, and then you get a type, and then type says line, for instance, and then all your coordinates. And then if you load that into Python or a GIS system, it knows what to do. Actually, all of those various types work like that. But some you can open very easily using a text editor, so you can interpret it, you can look at it yourself and verify that it's correct, like GeoJSON. While a shapefile is much more difficult to open in a text editor, but you have to use software for that. KML, for instance, is used by Google Earth. So a lot of people work in Google Earth and then send you KML files to say, hey, this is the area that I want a satellite image from. Here's the KML, and then you have to provide the image. They have to know how to open. What's important is that especially shapefiles, they do have limitations. So they can be just, let's say, 1,000 ordinals long and not longer. Or they have certain shorter names. That's important to keep in mind, that you use the correct version. So that's for the vector. Yeah, a raster, that's what we have seen yesterday, all day, or you've seen it on Tuesday as well. That's our image. In the simplest form, it's just a matrix, right? We have an x-axis, we have a y-axis, we have our pixels, and they have often, in RGB, they have 3 values, and that's giving us our color. It's giving our resolution in space as well. And you can have stacked rasters, right? I guess that's discussed already on Tuesday, so you can look at it also in 3D. So this is 2D, of course, but today we're going to look a lot at 3D. So you have a band with an X and an X and a Y coordinate, and there's one version that's the blue band, another version that's the green band, a red band, a near infrared band, so you have a 3D matrix. Sometimes we even have more than 4 bands, and that's often multispectral. That's like the Sentinel data, something we're gonna look at today. What can you do with matrices? Well, the things I discussed yesterday. You can do filtering, right? That's how we stopped yesterday. You can sharpen your image, or you can smooth your image. You can do those edge detections. You can clip spectrally, that means on certain values. So spectral values that you found using your sensor. And you can do all types of image analysis, as we'll discuss after this slide. There are a lot of file formats again. So that's, for instance, JPEG 2000, right? I guess that's the one you're going to use. But another very common one is GeoTIFF. So it's a TIFF image, but it's geolocated. So instead of just pixels, you also get something extra that's incorporated in the file. That's saying, okay, my image is located as this latitude and this longitude with this rotation, and then your system, your software knows where to put it on a map already. So that's included in your GeoTIFF, and that's why it's called Geo.
So each pixel is located with the left long and rotation?
No, it's a bit easier even. So you can calculate that information if you know, for instance, the upper left corner. So you know one point, and you know how it's rotated, and how it's sometimes also skewed. You can catch actually in 6 variables, and that's called a zero transform matrix. So that's all you know, all you need to know, if you know the resolution, of course, as well. So if you know the distance for each pixel, then your system's knowing, okay, it has to be like 5 meters to the left is my next pixel center. Then it's what I draw. So that saves a lot of storage, of course. Of course, here that's something that Francois, I guess, already discussed with you. Compression is of course important here. You can have lossless or lossy compression. Yeah, this is what I just said. So the spatial reference, which is this transform matrix, or the information where your image is located on Earth. In the GeoTIFF it's included, but if you use PNGs or JPEGs, then often you have a separate file, a JPEG.xml, for instance, that is containing the metadata. So the data that's accompanying your image, that's telling your software package where it is. So then you have to be aware that you have 2 files that you have to use if you want to locate that image in time. If you already have, for instance, several JPEGs, of which you know they have the same location, then you can of course disregard it and just do your time analysis, for instance. Alright, what's important is that you can go from a raster to a vector, and from a vector to a raster. And we call those rasterize and vectorize. Right? That's, the terms in English are really, really good. So we can get from a raster, so this is an example, this is our satellite image, for instance, right? So we have a square here, and we have the church tower there. If we ask our software package to rasterize that, it's actually an example from the tutorial of ArcGIS, which is a commercial package. And you say, I want a simple version, then it's just drawing the line here. So it's looking for the straight edges using edge detectors. And then it's saying, okay, this is indeed a square, and the only thing then you have to store are those 4 coordinates. For the blue one, for the pink one or the purple one, you have, in this case, for the simplified output, you get 3 coordinates. You can also say, oh no, I don't want a simplified version, I don't want straight lines, I want to have the exact pixels followed. Then you get the non-simplified output. What you see is that where here 4 coordinates were enough to describe our rectangle, here you have like 1, 2, 3, 4, 5, I don't know, like 30 coordinates. That means that your file here is 8 times as large. Has more information? I'm not sure. Yeah.
Why the in the middle one, the triangle thing?
Yeah, the triangle. That's a good question. I guess that's something from the algorithm. So if you say simplified here, it's what simplified is doing is looking for the least amount of coordinates that are necessary to describe the form. I'm not really going in depth in that, but here, for instance, here it's very clear it's a rectangle. But here, actually the algorithm thinks, okay, it is a rectangle, but I can describe this using 3 coordinates, apparently. And it has to do with the distance, like remember the resampling we discussed yesterday, right? So you had like, you turned your image and you put, with the nearest neighbor, you put one value that in the pixel that's closest to it. Something is happening here as well. So you look at the distance between the coordinate, and remember this is just one coordinate. In raster language, this is just, okay, this is x is 5 and y is 4, right? So you have only one coordinate. So my algorithm doesn't know that this is a square, the simplified. It's only looking at, okay, I have one coordinate here, and the simplest way to make a polygon out of one coordinate, what is the simplest polygon? It's a triangle. Right?
Maybe because you use the same like algorithm of the big picture.
Yeah.
That is key point.
Yeah.
Because
So
that one we have just only 1 pixel.
yeah. So
And you just average or manipulate something between the nearest or the close of that pixel.
yeah. So here indeed, that's correct. So here you see it's one big group of pixels that are together, and all those points. So you see that there's no hole in it, right?
When you run the code,
Yeah.
the code run all the things in the same on pattern.
Mm-hmm.
That's the key.
It's looking for the pattern. Yeah. Yeah.
Same thing. Otherwise you got the wrong calculation of that pixel.
Yeah.
That's key.
And here there's actually no pattern.
Yeah.
It's just one point. Well, here you say, okay, that's actually interesting. Probably the non-simplified output, it's not taking into account this as 1, but it's taking this into account already as a square with 4 coordinates. And then you cannot simplify it anymore. Well, here you say, okay, there's 4 coordinates, and you combine it. It's something that software can really do very well. You see here, this is I think this is really interesting for you. So this is for instance, the border of a province, right? You can say, I want to rasterize my border, and I want to make either a line or a polygon, and you see the difference, right? So here in a line rasterization, really the line is followed, and you fill every pixel that's crossed by the line, but nothing more. So that's it. So you only get the boundary. It can be of interest, but often you're more interested in what's within the polygon. And then what you do is do polygon rasterization. You see that all pixels here are then filled already, and you see that often the good algorithm just disregards those pixels because they're just outside of the complete shape. So you see that this is a single vector, it's 2 small polygons, but it's only keeping the biggest one. And now what you can do, as we will see later, you can put this on your satellite image and only use those pixels. And then you can analyze only the region that you're interested in. So those are
So you mean when you calculation, you have the maps. You create the grid first, right? Something like that, and you get the image. Put it in binary something, put it together in order to know what exactly point in each pixel, and then you generate the code.
Yeah.
Calculate all the things.
Yeah. So you generate the coordinates. So this has coordinates, of course, but the algorithm calculates the coordinates that are in between in the raster.
As something yesterday, this one is uniform grid. It means the distance between each of them are equal for the whole picture.
Yeah. For the rasters.
Right.
Yeah.
But then you improve by using non-uniform that goes with the things of the pixel that you interested in, instead of the big one that that.
Yeah.
You know.
Yeah. So that's more like you clip it, indeed. So you're not interested in the whole image.
Yeah.
You're only interested in like a certain part, for instance, of your country. Then you can use this technique to cut that out. Yeah. And if you have like a raster with a higher resolution, then your squares are smaller, and you will see that here this is really blocky, right? So you really have this corner. If you have a better spatial resolution, then this corner will be much smaller and it will follow your line better. But of course, it is a vector versus how small. You can go very small, but the more, if you zoom in, you still will see the corners, while with a line, you only see the line because it's drawn as a line. So that's something to keep in mind. Let's see. So, the reason we're all here, we want to know what's in our image, right? We want to classify the information that our satellite is recording. And that's what we call image classification. All the things we discussed in the last days are combined in image classification. Because, like I said, we have multispectral data. We have R, G, and B bands already. So we have the three-dimensional space where we can look into combinations of those values that are unique for certain classes. For instance, water versus fields versus forest versus city. Right? That's a very common example. We have seen that each type of surface on the Earth, ground cover, can have its own unique spectral response. And based on what we call spectral signature or spectral fingerprint, we can then do the classification. I'll show you an example of that. If you want to assign each pixel with a certain combination of those bands to a group, then we call it clustering. And there are two types. In general, we can do that supervised, meaning we as users tell the computer, tell the algorithm, this is, for instance, the spectral signature that belongs to forest, and now give me all the pixels that are similar to it. Or exactly the same or slightly similar. There are different methods that we discussed. You can do that with multiple groups, and you already tell it up front how many groups you want to have. And all pixels are often assigned to a group, although you can set thresholds there and not assign it. Unsupervised, it's something you do not give the computer any information. You just give it the image and let the computer do its thing. And that's why we call it unsupervised. You do not look at it. There are, of course, settings that you have to provide to do that. So there are two terms that are very important for what we call this type of classification, pixel-based classification. And those are feature space and mixed pixels. And feature space, I guess that's the most important term of today. Because I'm going to repeat it all a lot, and also this type of image you will see a lot. What is the feature space? It's a scatter plot where the easiest way for us humans is to look at the scatter plot in 2 dimensions. For instance, we have a satellite with near infrared and red. Then we can put all the values, all the pixels of our image in the near infrared and the red axis. So let's say our image here on the top right corner has a red value of 4000 and a near infrared value of 2000, right? That's the radiance or the reflectance. then the pixel would be in my plot here. And if I do that for all the millions of pixels that are in my image, you often already see clusters. So you see unique combinations of, in this case, the near infrared band and the red band. And that's the way that you already visually can see, okay, this region of the combination of information is what is the unique signature of my value. What we are going to discuss today is what you put on those axes. So you have RGB, right? And you can put R and G here, the red and green bands. You can also have an axis sticking out of my screen with a third version, right? You get a three-dimensional space. You can also do this with 10 bands. It's too difficult to imagine for me, but you get 10 bands and the computer can classify it. But you do not only have to put the colors or the bands on it, you can also do transforms on your data. For instance, principal component analysis, where you look at other axes. So you do not look at the color axis anymore, but you look at the axis that has the least variance. That's something I'll explain later. So here, for instance, if we look at a pixel region with values that have very low red and very low infrared values, and we actually color them red here, then you see that already a large part of my image is classified. What is it? It's water. Because water is absorbing all infrared and all red. Right? If you look at the sea, it doesn't look red, so it's not reflecting red, it's actually absorbing all my red. And that's a very common way to classify certain pixels in one image.
What's the unit of the?
Yeah.
Of the,
I think
X and
this
Y?
is. I think it's reflectance multiplied by 10,000. So it's just actually. I think this is top of atmosphere.
No. The unit. What is the unit?
Here.
Yes.
Yeah. I guess it's probably radians.
Radian.
Radians. So the brightness of a pixel. Actually, that's a good question. It's not that important what the unit is, because the techniques are not interested in the unit here anymore, because you only want to have the clusters. So the unit is important for your own interpretation, but it's not very important for the clustering. As long as, for instance, here they are in the same range, right? So this is from 0 to 8,000, and this is from 0 to 10,000. You're like in the same range. You can see that there's actually kind of a correlation for some pixels that are very that are high in red reflectance and high in near infrared reflectance.
I think I thought the red and the infrared is the frequency is close to each other. While in a pixel or in one place there will be like something that have like high in red but low in infrared.
I'll show you. This is the most used classification algorithm. It's called NDVI, Normalized Difference Vegetation Index.
Or if you say that you have another exit that stick from the board and it's different color like blue and the X exit is what is infrared too?
In this case, we only use two axes.
No. Like if you have like another exit, like if you have a blue color, and what is the other exit?
Then you can use blue. You can use blue, red, and near infrared.
You can use like blue and infrared
as well.
That's even stranger because blue has like so much different frequency than the infrared.
Yeah, that's exactly the point of this. So you want to have them as you're looking for this combination of bands where your clusters that you want are the easiest to detect. So if, for instance, a pixel with water has no reflection at all in near infrared, right? While it has a lot of reflection in blue, then it will have a certain combination, right? It will be somewhere on the spot. If this would be blue, and it has all my water pixels have that same cluster, right? But let's say vegetation, it reflects near infrared. So that will be high here, and it's not blue, it's green. So that will be here. So then we have a cluster of pixels there, a cluster of pixels there, and a cluster of pixels there. Then we only have to do, the only thing we have to do to say, okay, what is then water and what is then not water, is take a line here, say, okay, everything to the left of the line is water, and everything to the right is non-water or vegetation or something like that. I'll show you. This is very good questions. So that's the core of today. So the only thing we're looking for is how to make our feature space so that you can define clusters. Let me first explain mixed pixels and then we go all the way in, okay? What's important to remember is that we are using a certain spatial resolution, right? So we have a pixel, let's say of 30 by 30 meters. But of course our objects are not 30 by 30 meters. There are a lot of objects within this pixel. If you compare this image to the similar aerial photograph of 1 meter, then you see that indeed the general sense is similar, right? This is light, light, dark, dark. But there's a lot of nuance here that is not present there. That's what we call mixed pixels. We always know that within a pixel there can be mixed classes. So within a pixel, let's say the border of a forest and a road. You never know exactly where your road starts and where your forest ends if you are having in one pixel as well the information of the reflectance of your road and the reflectance of your forest. And that's what we call mixed pixel. So the number, the digital number, so what your camera records will be a combination of the reflectance of forest and the reflectance of the road. And the coarser your spatial resolution is, the more difficult it is, the less easy it is to get the edges of your features. You, for instance, see that in a lot of urban environments where, of course, there are a lot of different items in a small region. So you can have a road, you can have trees, you can have a garden, you can have a house, all within one pixel of 30 meters. While in, for instance, forests are not smaller than 30 by 30 meters. So then it's much more easy to get one pixel that has the correct value. Why is this important? If you are going to train your data, then you want, of course, to train it if you can with the best possible data. And the best possible data is not the one that's contaminated, that's mixed from your signal, but that has only, like the oak signal as I had in my example, right? You have oaks and pines. You don't want to mix pixels where you have the oak trees and the pine trees for your classification. You only want to have the pixel with the oak information and look for those pixels. So that's something to keep in mind. Let's look at feature space in a different way. This is a very general example. So we have a band. I don't know which band, it doesn't really matter, band X, and we have another band, band Y. And here you see that this, it might be red and green, right? Because we're in 8 bits, we're between 0 and 255. And apparently water is reflecting medium on this band, while it's not reflecting anything on that band, right? All the pixels. So you say this is a group and it belongs together. We see it now easier because I already colored those dots, right? But if you would look at it without knowing the color, you would already see, okay, this is a cluster, this is a cluster, this is a one cluster, and this is one cluster, right? If you look to it without any color. But we know what it is. So then, if you also put this, so this might be your training data, then you know that this is wheat, so that's a field of wheat, well this is grass. So this is probably a bit more lighter green than that one. The same holds for houses versus their soil. So apparently, if we now, for instance, draw circles, then this can be a circle, this can be a circle, this is one circle, this is one circle, this can be a circle, and that can be a circle, right? And then we say, okay, everything that's within this circle belongs to water. So each pixel with this combination of bands is water. Here, it's a bit more difficult because there is a bit of overlap, right? So where do we put our border? That's the essence of the classification algorithm. And that's where some algorithms do better than others, depending on your data. And that's something that you will have to test. And that's also why you have to know some ground truth data. So you sometimes go out, use other data sources like drones or camera images or other reports that you have, and look how you can make this border as good as possible. Yeah.
On the x and y axis here, this is from 0 to 255.
Yeah.
So this is the light intensity. And
This is, yeah, this
compared with the previous slide is from 0 to 10,000.
Yeah, so this is really, for instance, the RGB value that you use. Just some 8-bit information point. You can also have, if you use reflectance, it will be between 0 and 1. And here as well. But sometimes you are comparing.
Reflection and light intensity.
Yeah, the light intensity is the radiance, like we discussed yesterday. So it's really the light that's coming into a surface, while the reflectance is the light coming into a surface and reflected of it. So here, this one is, sometimes it's even scaled, so that's what I use, you will see later as well. Sometimes we do reflectance between 0 and 1, sometimes we do it between 0 and 100, so we say it's percentage. Sometimes you can do it also between 0 and 10,000, it's just a multiplication in that sense. It's not that that the values are affected by it, or that the classification algorithm has struggles with it. So is this concept kind of clear for you with the feature space? So remember that all the things, especially in the afternoon, I'm going to show you a lot of applications. Then sometimes you do so many processing steps to your data that this is not very easily recognizable anymore as the red band. It can be the 8th principal component of my red, green, blue and near infrared band. Oh, then it's probably the 4th principal component. But you can do all those transformations just to be sure that this cluster is there, that there's no overlap. So with all those transformations, let's say all my pixels were grouped. You couldn't get them, you couldn't by eye even distinguish a cluster, right? That would mean all those pixels would be like laying here, those as well. Then you would have the wrong combination of bands. And you have to look further and think about which types of bands can I then use to actually get to this image. And that's the whole thing we do. And that's something that, yeah.
If we use the another dimensional.
Yeah, you can, yeah.
To take out more.
Yes, exactly. Then it's going to be easier. The good thing is with the computer-powered analysis that I'll show you, we do not have to do this ourselves. We are not going to look at this. We let the computer tell us, okay, this is the best method to separate those clusters. And that's the best thing of it. But let's start with supervised classification. So here in supervised classification, we as users tell the computer this region of our satellite image is forest. This region is water, this region is a city, and this region is road or bare soil, right? Then that's what we call training sites. So you have to know this by either going out into the field or because you look at an image and you're really certain that some pixel belongs to a certain class. What we then do, the computer actually calculates a signature or a fingerprint based on the information that is within the sites that you selected. So let's say if I this a little bit. If we have our image here and there's a large lake here and there's a city here, what we then do is and okay, there's a forest here as well. You say, okay, this part, for instance, I'm really certain it's water, right? That's you draw. You make a vector in the system. Here as well, you say, okay, this is city, I'm certain, and this is forest. What then your computer does is, okay, it says, okay, this is, those are, let's say, 5,000 pixels, because it's a large image. It can calculate the mean of all those pixels, and the standard deviation, you know how far away it is. Oh, that's my computer actually, right? So we put that. There we are. Here as well. So you calculate the average, and then it's looking for there we are. All right. Then we compute the mean, for instance, and then it's gonna present, put this on top of the map and gonna look which pixels are actually belong to this class. It is right. Ideally, your classes do not overlap, so you do not have the mixed pixels. That they don't overlap with other classes. And here as well, so you don't want to draw this one. If your forest would be like this, you shouldn't take that region, right? Because then there's confusion in your algorithm. And you're familiar with the saying garbage in, garbage out? Yeah, right? Well, that's what you get. So garbage in means your training data is not good, it's garbage. Then your classification will also be not good, will also be garbage. So that's why it's very important to really be sure about your training data. What you can do is, okay, you select training data, you let the computer assign the pixels to certain classes, you evaluate it, and sometimes you are happy with the result, and sometimes you are not. That happens actually, most often you are not happy with the result. So then you have to retrain it and say, okay, maybe I'll have to take more data of this, say, of the forest. Because forest can be having different tones, different colors. There are different types of forest, but you only want to know forest as a general group and not the oaks and not the pines. Then you have to include the pines and the oaks in the training data for forest, right? So you have to be sure that you take into account all this type of information. Yeah, this is it's a bit more elaborate. It's more for you as a backup in your slides. I just want to highlight some. So be sure to have the full range of variability. That's what I just explained. So be sure to have all the different types of trees that you have in your forest. Or if you are city, if you want urban developed regions, be sure to include industrial regions and urban city regions and assign those to the classes. This is important. You are allowed to select multiple sites per training type, right? You can just draw boxes all over the place, and maybe if we have time in the afternoon, I can show you how to do it in QGIS. Maybe are you going to do it, Mark, tomorrow?
I don't know if we have time.
Okay.
That's the only issue, but I would try to.
It would be nice to have an example maybe in Snap. Yeah, this is the most important part, the last one. The more time you spend on having the right samples and right training sites, the better your classification will be. Right? So sometimes I just take a week to go to a measurement institute to measure samples of earth, of different types of earth. So of sand, of clay, of bricks, and that's something I use as input for my classification. Because I cannot see with my eyes from an image what part of the region is of my satellite image is sand and what type is clay. Because the differences are so small that if I just calculate from another source, like the spectral signature, and then apply this as a supervised classification, then it's much better. So sometimes it takes time. Alright, we're almost at an example, a bit more text. So what type of distances or measures can we use to determine which pixel belongs to which group? There are a lot of those types, and I highlighted 3 that are very common. You can have minimum distance, so that's actually the closest distance. You can look at maximum likelihood, which is a statistical term.